and we'll start from current slide. Okay. Now, before I do any more on what Chandra was asking, let me make these few announcements. Okay? Now, this pertains to two of you that are here, one that's not here. Wish you were here. Maybe you'll still come in. And it may have been taken care of because I made these notes last week, either Thursday or Friday. So if you've taken care of it by then, fine. But the vice president came out with a memorandum sometime last week. Okay? I think it was either Thursday or Friday of last week. I heard about it and reviewed it then. He said to print it and read it to you in class. But last August, my printer started losing toner. So I couldn't print very much. So I would shake it, and I could get a few more pages, shake it. I ordered a new toner, in fact, ordered two in August. Well, they still haven't arrived. And I've shaken the toner so much I can't get any more out of it to speak of, maybe a little bit. So I couldn't print the thing off to read to you, so I'll basically tell you what it is. Tomorrow, we love you tomorrow. Tomorrow is the last day that after tomorrow, they're going to remove all students who have not completed payments from the rolls, okay? And I know three of you in here, I know some, the situations, we're not quite able to complete everything and waiting on paperwork or whatever. But please try to get it done today or tomorrow. If you can't get it done today or tomorrow, please let someone in the business office know. That could be the cashier's window, business office, somewhere. Let them know where you are in the process, that you're still waiting on this one piece of stuffing or that or whatever. So if there is a way they can put a flag and keep from removing you from class, that would be a very good thing. Okay? So please, folks, try to get that done today or tomorrow at the latest, because I think it's after 5 o'clock tomorrow they remove all unpaid students, unless they've heard from you somehow. I'm not even sure that will work, but it's worth a shot. You'll be removed from the roll. So one person who should be hearing this is not here, and if he doesn't come in later today, it'll be, he may not hear about it before they remove him tomorrow, and I hate that. Here is the other thing that I want you to do, though. You may know of people, even though you may be paid, you may know of people who have not completed payment. Please let them know that they will be removing people from the roll as of the end of business tomorrow. Okay? So that's number one. A pretty minor thing. Normally on Fridays, my office hours are 7:45 to 11:45. Well, tomorrow, on Friday, they've called a meeting for 12:30. So that means my office hours won't be shortened. They'll actually lengthen, because I'll be there from 7:45 until 12:30, or close to 12:30. Then I'll go to the meeting, and then I'll be going home. So actually, I have a few more office hours, 45 more minutes of office hour, 30 to 45 anyway, than I normally would have. So if you need to see me before 12, I'd say before too late on Friday. All right, here's Unhealed. Okay. Now, sorry I've already announced this, but just wanted to let everybody know. The Vice President has said, and this is in case you know of anyone that falls in this boat, okay? The Vice President has said that they will remove unpaid students from the roll tomorrow. So if you know of anyone who hasn't still completed payment, please encourage them to get it done today or tomorrow. Or let someone in the business office know what the status is and how close you are, whatever, from having that payment completed. And they may be able to put a flag on it and not remove you from the roll. I don't know if they can or not, but hopefully they can. All right. And then LaShonda was asking, I was going to go over this anyway. And I started talking about it before Screencast-O-Matic came up, so I want to get those in first. Okay. On Thursday, we finished chapter 18, and we had the lab on 18, which I assume you didn't get a copy, right? Okay. Is anyone else who didn't get a copy of lab 18? It's not lab 18, the lab for chapter 18. Just one? Two. Okay. Yeah. All right. Now. 3. Okay. Anyone else who did not get up? Lab 18. All right. Now let me review a little bit about lab 18. Very short lab, okay? So therefore we have to extend it a little bit. But if you listen to the YouTube video from last time, you will hear us go over the lab. You'll hear the end of chapter 18, and then you'll hear us go over the lab. What we did in the lab was collect data and do measurements and calculations, and we got the density of a piece of granite, and we got the density of a piece of basalt. Okay? So you should be able to hear all that. If you can't hear it all on the YouTube video, get with someone who hasn't turned them in yet. Okay? So that's on the back of the lab. Only 6 entries there. Okay? You should be able to hear that and fill them up. Then in the middle of the lab, you'll see 4 questions. And I went over most of those with you. So do that too. That's 4 more. That gets you up to 10. The lab's worth 25 points. We've only got 10 points worth here. So the next 15 points you can earn or get by doing any 15 or more of the questions for thought or for further analysis on page 478 in the new book. If you got an older book, it's in the end of that chapter. There are 20 questions there. 16 questions for thought, 4 for further analysis. Pick any 15 or more. If you want to do an extra 1 or 2, in case you miss one, you still have a chance to get all 15 points. So any 15 or more of those 20 questions, do the answers. You don't have to write the questions if you don't want to, but what I suggested was write QFT, that's questions for thought number 6 or whatever you're going to do, and then answer that. And then FFA is for further analysis, number 2 or whatever. So that way I can tell which question you're answering. So get those done. Now, what I recommended, and I know those who weren't here, you won't have this opportunity unless you choose to postpone your test. I recommend that you try to get these answered before the test today, because that's a great way to study for the test, okay? But if you didn't get them answered, you can still do the test because you have a week to turn in the lab. And if you want to go and take the test today without answering the questions, you certainly can. That's up to you. You're adults. You can do whatever you want to. But if you did want to work on the questions before you did the lab, then you'll have to come in early on Thursday, or after the test, while others are taking the test today, you can be working on your questions, and then if you want to take it afterwards, you may have time to do it then, or you can come back. Tomorrow I've got office hours 3:15 to 5:15, though I do have the math team up here. So I won't be in my office necessarily Mondays and Wednesdays 3:15 to 5:15. I'll be up here in this classroom unless no one shows up for the math team, and then I'll be down in my office. So Mondays and Wednesdays, I'm either going to be up here in my office 3:15 to 5:15. And Tuesdays and Thursdays, basically, it's my lunch hour, which is 12:15 to 1:15, or at the end of the day. Okay. So, any questions on the lab? Okay. 10 points worth from the lab. 4 questions in the middle. 6 fill in the 6 things to do in your table. And then the other 15 or more questions from the end of the chapter. 18, that would be questions for thought and for further analysis. Total of 20 questions there. You choose 15 or more of them to answer. Okay. Now, where does that leave us today? Today we're starting chapter 19, Building the Earth's Surface. And this is a relatively long chapter, not super long, but I think it'll take most of today to do. We may not even finish it today. I don't know. It just depends on how long. I think we will. But I don't think we'll have time to do the lab today, because that would be 2 hours of this, 2 hours of lab, and 30 minutes of the test. So if we do finish the chapter today and don't have time to do the lab, then we'll go on and get started on chapter 20. Okay, so we'll see what happens with that. All right, does that answer pretty much what you were asking? Okay, and that's where we left off. All right, now since at least one person has come in since I last said this, let me say it again. There was an email that came out from the vice president late last week. It was either Thursday or Friday. I don't remember which day it was. And basically, it said to print it off and do. My printer's not working because my toner's out. I've ordered more back in August, but it hasn't come in yet. So I couldn't print it out. But basically, here's what he's saying in that email. Any students who have not completed payment are going to be removed from the roll tomorrow, okay? In the business tomorrow, I believe is what it said. So if you haven't, or if you know of someone who hasn't completed their payment, please get that done today or tomorrow, okay? Or if it's not possible for you to do it today or tomorrow, then please go by the business office. That's our cashier's window on this campus. If you're over on the other campus, it's up on the second floor of the A building, administration building over there, and let them know, what your plans are, that you're working on it, that you hope to have it by thus and so day or whatever. They may be able to put a flag and keep from removing you from the class. I don't know if they can or not, but it's worth a try. All right? And did I mark you when you came in? No, I didn't. Sam's here. Does anyone else come in since I called roll? Here's one more. All right. Chelsea's here. And I think you probably heard it in this morning's class about the removing people who haven't paid. Did you hear that? Yeah, okay. So you've already heard it. So I want to make sure everybody's heard it, so that now that anyone else who came in need a lab from last Thursday. Everybody got one. Okay. Okay. Any other questions before we get started on today? All right. Today we're starting chapter 19. Okay? Now, as I was saying before, we'll probably do 19 just about all day today. If we finish it before time for the test, which would be at 5:15, then we'll go on and start chapter 20, because I don't think we're going to have time to do the lab for 19 today, because we'd have to finish the chapter in 2 hours and then do the lab in 2 hours. It's not a very long lab, but it is one that I want to give you plenty of time to do.
Wait, we got a test on with chapter 18 minutes?
Chapter 18 test is today, the last 30 minutes. So if you don't have your formula and equation sheet already, be working on it. talked about it last time, when we finished the chapter. And I said the thing about get your questions done because the test will be on Tuesday. If you can get the questions done before the test, it'll help you study for the test. All right. So building Earth's surface. Anyone know what that is? Yeah, that's a volcano. Not quite coming out of the cone or the crater like we think. This is coming down the side. I don't know for certain, but I would almost bet you this is from Hawaii because that's how most of the Earth volcanoes look. The one in the in my old text, the one in the new text, this one in the old text doesn't have a caption on it, but this doesn't say where it's coming from either. But I'm betting it's Hawaii. The most active volcano in the world, as far as I know, is the Kilauea volcano in Hawaii, on the Big Island, Hawaii. And it's been erupting almost continuously for years, maybe decades. I don't know how long. It just sort of spews lava out. It doesn't erupt and more, it just is leaking lava almost continuously. That's what making the islands there, okay? I know about Kilauea because you may find this bizarre, but it's true. They name ammunition ships, that's what I was on in the Navy, after volcanoes. Okay, I think that's because if you ever do have a fire on board, you're going to leave a huge hole in the water, So we were very careful about fire. Okay, very careful about fire. So anyway, the core concept, which is on that first page as well, the surface of the Earth is involved with plate tectonic processes. Yes, that was chapter 18. That result in an ongoing buildup of that surface. We just saw the picture of volcanoes. That's Earth's surface being built. This is a picture, I think, of Mount Shasta in Northern California. I believe it is. I believe it could be right in here, but I think it's Shasta. This is a volcanic mountain. You can see the old lava flows here. It hasn't erupted in probably decades, maybe since we've even discovered it. It's been inactive for a very, very long time. You can see sort of the crater here. Last time it blew part of the crater off, it looks like. So it's up there, but it's not active right now. But when it was active, it was building Earth's surface, just like you see here. That's not the only way Earth's surface gets built, but that's one of the ways. So that's the core concept of this chapter. How is the Earth's surface being built? And it's being built continuously. So the first subtopic here, or I guess topic, would be interpreting the Earth's surface. And one of the principles that informs this, I guess you would say, is this one, the principle of uniformity. Basically, the shorthand for it is the present is the key to the past. Okay? That's sort of a strange-sounding statement. Here's what that means, or one of the things. Rocks are being changed today by the same processes that changed them in the past. So what you see happening now is reflecting what happened in the past as well. Prior to this becoming the current thought of it, the old idea was that there were some catastrophic events that shaped the Earth's surface, and since then it really hasn't been shaped much anymore. Like major volcanic eruptions and all sorts of things going on, and not much has happened. Well, we know that's not true. Stuff is happening continuously. And what the current thought is, it wasn't just a bunch of catastrophic events that basically shaped the Earth and then we've just carried on since then. It's that what's happening today was happening before and will happen again, okay? It's the principle of uniformity. The catastrophic events contribute, of course. There are still volcanoes, I just said. Kilauea is still erupting, yeah.
Because history repeats itself, right?
Yeah, yeah, exactly. It's the same type of idea, except this is the fiscal, that's the human input. Usually we think of history, but yeah, it's the same type of thing on the fiscal world. So there have always been volcanoes. There will still be volcanoes. Okay? There have always been earthquakes. I just heard, was it this morning or yesterday, that there was a minor quake somewhere in California. Okay? No damage. They recorded too much, but there was a fairly minor earthquake there. There have been and continue to be meteorite impacts. Okay? It's happened before. It'll happen again. It's happening today. So, yeah, these can be catastrophic events. This isn't saying they don't happen, but it says the Earth wasn't shaped by a bunch of catastrophic events and then nothing else is happening. Whatever is happening today went on before and will, as you say, repeat itself and happen again. Now, in a couple chapters, we're going to be talking about weather, and there's a lot of argument on this. Weather is a natural physical event, but that can be shaped and influenced by what man has done, or at least it sure seems like it. We have just had two of the most powerful hurricanes hit the U.S. in 1 year that has ever happened before. They were both, I think, Category 4s when they hit the U.S. Yeah, and it's hitting Puerto Rico today. Dominican right now, and it's Category 5. And both of those others were Category 5s before they hit. But when they hit the U.S., they were Category 4s. Very powerful Category 4s, because they had been Category 5s, and this new one could easily do the same thing. And we just missed another one that went up the East Coast and dumped a lot of rain, but it didn't hit the U.S. directly. So, not going to say that things we do don't contribute, but that's weather. Okay. How about earthquakes? Do we contribute to earthquakes? What's that? Okay, specifically a current form of mining that's called, what is the name of that? Fracking. The fracking has, since they have been doing the process called fracking in the Midwest over the last decade or so, they have way more increased the number of earthquakes they've recorded there. And I think the consensus is what we're doing is contributing to that. And here's Ashley. So even these physical events like earthquakes, now I don't think we've ever, and we hopefully never will call it a major one, but we certainly can, in some small ways, affect those. Now, remember I said Iceland heated most everybody that lives there with hot water they pump over the rocks. Well, they decided to get a little bit better system of doing that by drilling down into that hot rock and getting more volume of water and that kind of stuff. When they did either the drilling process or they hit a weak thing, they almost had a major volcanic eruption because of their effort. They sealed that one off as soon as they could and went back and either did something a little safer. But I'm not saying we couldn't contribute some things to it, but generally these things happen on their own. Okay? So, another term. This is called diastrophism, I guess is how you pronounce that. Okay? And by the way, the previous one, principle of uniformity, is also called uniformitism. Uniformitarianism. Okay, so it's a very long word. But diastrophism also is another closely related topic, and I don't even see that in the new text. It was in the old one. Have you found it?
No.
Oh.
If we finish chapter 19 today, will we have a test on the Thursday?
Yeah. Okay, but wait. No, I'm trying to remember. No. I'm pretty sure that 19 is the one and only one chapter that you have a take-home test. So no, we won't have a test on it, but if we finish it today, I will give you the test to take home. You have a week to work on it. I just did not like the questions they had, the options they had in the back of the book. I mean, in the test bank, not the back of the book, but the test bank. I thought the choices, the way they worded them, were pretty vague and unclear. And so I changed it and made a short answer test. But because it's a short answer test, I wanted you to be able to go through the chapter and find those short answers.
I'm just asking because I've been misreading my schedule for work today, and I got to leave to go to work, so I just didn't want to leave and
Okay.
With.
Okay, so you're going to have to leave early is what you're saying?
Yeah, I'm probably going to leave like right now.
Okay. Well, we'll have the test on 18 for sure at the end of the day.
Well, I just make it.
And then when you come back, I'll give you, because I don't think I have the runoff copies of 19 because I wasn't sure we were going to finish it. Okay. All right, but right now I'm trying to find diastrophism in the text. Yes.
I just looked in the glossary and it said that diastrophism was between pages 482 and 488, but I don't see it.
That's where it's supposed to be, and it was in the old edition. I just do not see it. So I think they may have removed it here. But anyway, it's fairly closely related. Diastrophism, okay, is the process of deformation that changes the Earth's surface. That's the definition of it. The process of deformation that changes the Earth's surface. And what follows this are features of diastrophism, okay? So don't sweat it too much. That wasn't one of the things on the test, so you don't have to worry about it. But that's basically the long and short. Diastrophism produces structures such as plateaus, mountains, and folds in the crust. We'll talk about each of those things, especially the mountains and folds. Not too much about plateaus, but pretty much know what it is. Diastrophism is related to volcanism. That's one of the processes that causes changes in the Earth's surface. Volcanism is the movement of magma from way beneath the surface up either to the surface or near the surface. It also relates to earthquakes, which we'll talk about in this chapter as well. It's the basic working theory that produces that diastrophism is plate tectonics. Okay? And that's part of the reason that what we see and the current thought is today is taking away. Before plate tectonics was a theory, they basically was thinking everything happened before and just little minor things are happening now. Plate tectonics say, no, things are still going on continuously. Okay? So that's the basic theory behind diastrophism and uniformitarianism. Okay? Whatever that word is. Okay. Now, here's the major part that we'll get at today. This is all illustrations of diastrophism, but we'll hardly use that word anymore. All right. Several ways I think of these things, and I'll give you a couple ways of thinking about it, and you choose what you understand best. Stress, I think of as sort of like a verb. It's the action. Okay? Strain, I think of as sort of the noun. That's the result of the action. It's almost like the verb and its object. Okay? Except it's a little different comparison there. So let's look at these two concepts, stress and strain. First, stress. Stresses are forces. That's why I say they're active. They're verbs. They're things that are happening. And here is Fred, right?
Yes, sir.
Okay. All right. Now, said I'd be pausing and doing this every time someone else came in, just because it's pretty important. He already knows?
Yeah.
Okay, about tomorrow being the last day for it.
Yes,
okay.
I got it. I'm on top of it.
Oh, okay. There'll be. Oh, yeah, you came in too. That's right. I missed it. Okay. The vice president sent around an email late last week. I can't remember if it was Thursday or Friday. I saw it Friday, I think it was. I haven't heard about it and stuff. And basically it said, he said to print it out and read it, but my printer's not working because my toner went out. I ordered it back in August and still hasn't come in. So I'm doing it sort of off the top. That any unpaid students still have not completed payment will be removed from the classes as of tomorrow. You have heard it too? Okay.
I think
Huh?
my financial obligations.
Yeah. But the reason I'm telling people is so that if you know of anyone who may not have completed theirs, please let them know they got to get it done by tomorrow. Today's better, but tomorrow's okay. Or if you can't, go by the business office, the cashier's window, somewhere like that, and explain to them what you're doing to complete your payment. Or, the people you know that may be in that. So that's the big news, the big thing that's going on. So, okay, back to this. Stresses are the forces, okay? The forces that either tend to compress, pull apart, or somehow change or deform a rock. Three stress forces. They love trees, don't they? Okay? First of these is compressive stresses. Now this sounds like your convergent boundaries in plate tectonics, and they are very similar. This is when the plates are moving together. That creates these compressive stresses, okay? These are the forces that are compressing the rocks, okay? You also have tensional stresses. This is when the plates are moving apart. That was like your divergent plates. So these are related very, very closely to what we had in the last chapter, which is what you're being tested on today. So this is not bad to go over. And then the third type of stress is what they call a shear stress. The shear stress is when the plates are sliding past each other. I really don't like that verb there because they don't slip and slide. They get hung up and, it's a rough surface and they then suddenly break. That's what causes earthquakes. So yeah, but it means when the earths are moving, the plates are moving sort of like parallel to each other. These are moving together, here they're moving apart. These are moving somewhat against each other, but neither apart or together. Those are called your shear stresses, okay? And that's like the transform boundaries. That's like the convergent boundaries, divergent boundaries, and I just said it, transform boundaries, shear stresses. So those are the forces, those are the actions, those are the things that are causing the result. What's the result? Those are the strains, okay? That's the adjustment of the rocks when the stresses are upon them. Again, they like three strain types, okay? The first of these is an elastic strain, okay? The forces are happening, compressive, tensional, or shear, and there's an elastic strain. That means, say, the rock is being pulled at, but when the stress is released, then the rock goes back to its original shape. Or it's being compressed, but when the compression relaxes, it goes back to its original shape. Or the rock is being, the plates are moving past each other, shear stresses, and when those are relieved, the rock goes back to it. That's what elastic is. Returns to its original shape. Now, I think that most of us, at least I do, when I see the term elastic, or at least I used to, I always thought, oh, that's stretchy stuff. That elastic was something that stretched. No, elastic is something that, when stretched, returns to its original shape. Okay? The paper clips that I used to use, that I usually use when I'm stapling things or fixing things together, send down there to be copied. Once they've been used over and over again, they don't return to the same tightness. They get too loose. They pass their elasticity. But the new ones and things, they clip on, they keep their shape and hold the papers together really well. There are many other examples of elastic strain. Now, this is the result of the stresses, the adjustment from the stresses. Next is the plastic strain. And I know that most of us probably think plastic, all that's the stuff that I bought my food in, or the drink is in the plastic bottle. This is plastic, you know. Everything's plastic. The caps here are plastic, whatever, are all plastic. Well, that's not exactly what we mean by plastic strain. The word plastic was around before we started talking about those products. But basically, what makes them plastic is the thing they can be molded or bent. So in other words, when you have the stresses, compression, tension, or shear, that then the object doesn't return to its original shape, but gets deformed, molded, bent, does not return to the original shape. Okay? That would be like a rubber band. You think of being elastic, and as long as it goes back to that same thing, but you know that after using a rubber band over and over, suddenly it's a little longer than it used to be. That's plastic. When it returned to its original shape, that was elastic. When it didn't quite go back to that shape, it was plastic. Okay? And then the third type of strain, result of the stress, the force, is a fracture strain. Okay? You've got these two rocks coming together from the compression, and rather than just deforming and then springing back, or deforming completely, they just fracture. Okay? With sound effects. Okay? Or when the tensional stress are doing, rather than just sort of stretching for a while, and then when it's released, they go back to the original shape, or permanently get molded or bent. This time they actually break. Same with the shear stresses. Rather than holding for a while and then going back to the shape or getting bent or molded, they actually just break. Generally, that's what causes earthquakes. You have a fracture strain. The rock cracks or breaks, disintegrates, whatever. It's no longer either returning to the original shape or just deforming. It actually breaks. Okay. So, possible material responses to stresses. This is almost strains, okay? But this is just talking about in general. They've added one here. One is no change whatsoever. In other words, I push on the wall. Am I deforming the wall at all? Not measurably, okay? I can push, that's a force, on the wall, but nothing happens. Now, if I were to push hard enough, and I do sort of bend that end a little bit, but then when I release it, it pops back, that would be elastic change with recovery. Now, especially when I do elastic, and as opposed to no change. What do you think when you say hit a baseball with a bat? Is that a no change? You just change the direction of the ball? If you were to observe, a slow motion shot of that bat hitting the ball, you will actually see the ball wrap a little bit around the bat, and the bat actually bend a little bit, but then the ball flies off, the bat returns to its thing. That's elastic. It's not a no change. No change from beginning to end, but there was change in the middle. No change at all is me pushing on the wall and not making a dent in it. That's the no change. A little bit better illustration of that would be a tennis racket on the tennis ball. I almost bet you've probably seen that. But when they tennis players, some of them can really whack at those things, those balls. And if you were to take a picture of that, that tennis ball actually gets awfully flat because that racket does flatten that ball a lot. Not only that, the ball makes a bulge on the backside of the racket. But then, when they complete their shot, the ball returns to its shape, the racket returns to its shape. That's elastic. Okay? Now, plastic change with no recovery, I think we already pretty much beat that to death. But that's when you stretch that thing and it doesn't come back anymore. I don't know if you've ever had a spring. I have one in my briefcase. Sometime or another, the STEM program was giving away these little flash drives. And the guy gave me one, I put it in my book bag. They were really cheap. That's why they were giving them away, because in no time, just being banged around in my book bag, the cover came off, and there was a little spring in there that would push the thing back and forth. It got sprung. That spring didn't return to its original shape. That was plastic. Okay. Or they break from the pressure. That's the fracture. So the elastic was on the last slide, plastic was on the last slide. Breaking, that was fracture. These were the three listed before. The only new one here is no change at all. There is a stress, but it doesn't make any difference at all. Now, why would a rock, R-O-C-K, not country, a rock, why would a rock have different responses? Well, four different things here, too. The nature of the rock, okay? For instance, what's the chemical composition of the rock, okay? Is it things with very strong fixed bonds? If it is, you might have a no change situation. If it's pretty strong but not as strong, you may have elastic. If, however, it was fairly weak bonds to begin with, it may have some plastic change with no recovery or may actually fracture. So the nature of the rock will have a lot to do with this. Okay? Now, that's one thing. I said the bonding and the materials that make them up. But also the brittleness of the rock. Remember when you did the lab on the physical properties of rock? What was that? Minerals. Rock, I believe. No, minerals. Physical properties of minerals. That lab that we did a while back, there were things like crystal structure, fracture, and there was also hardness. The harder the rock, maybe the more likely you have no change at all. It may be if it's pretty soft rock, it may have plastic change with no recovery.
And that depending on the pressure you get though?
Yeah, okay, yeah. Now that's coming in later. Okay. So the nature of the rock, that would be the materials that make them up, the bonding strength, and then the other characteristics like the fracture and the hardness and that kind of thing. then you also have the temperature of the rock. Okay? Any of you work around or have anything to do with the steel industry? I thought at one time someone had, okay, it was Sam. Okay? If you heat rock hot enough, you are going to, it gets a lot more plastic. Okay? In fact, it actually melts. Okay? In fact, if you think back, our metamorphic rock, you added heat and pressure, you actually changed the crystal structure. So now it's a harder rock. It's a more brittle rock or something like this. So the temperature of the rock certainly does change. As that changes, then so does the characteristics of the rock. The speed of the stress application. Okay? I can take this pencil here and I can very slowly add a little bit of force to it, and I can probably, because this is plastic, bend it a little, but it comes back elastic with recovery. But if I did it real suddenly, I'm going to break it. Okay? I don't have a wooden pencil up here, but you can see that bend there. That baseball bat, if you hit the ball with it really hard, if you hit it right, it's going to pop back, elastic. But if you have it turned a little bit and you hit it on the grain, you can fracture it. I think Bo Jackson was pretty well known for fracturing a few bats. Okay? So yeah, the speed of the stress application, that could change whether it's plastic, elastic, or fracture. And then you mentioned the pressure, the confining pressure. If you've got pressure from underneath, but not much pressure from on top, you're going to change the rock. Probably plastic change, okay? Possibly breaking. If you have pressure from above and below, you could change other things about the rock, like the crystal structure and things like that. So whatever your confining pressures are, or not, those rock variables will determine which of these is going to happen. Same rock could undergo, with different temperatures, pressures, and other things, could have different responses to the same stress. And then, as I think you were sort of hinting at, the interplay between all four of these, just a little bit of change here and something else changes it. Yeah, in the speed, yeah, you can have very different outcomes. Interplay produces observed rock structure. Unless, here is a graph, this is a fairly typical kind of an engineering type graphic that you see not just in physical science, but you see it in some of the other strengths of materials and other courses you might, if you're going into engineering, something you might run into. We have two different substances here, A and B. Both of them undergo stress. That's the force. Now, for you who are pure mathematicians, I'm sure several of you are, generally, what goes on the horizontal axis is the independent variable, and the dependent variable goes on the vertical. This is kind of backwards from that, because the stress is the independent. That's what you do to it. The strain is a result of stress. Strain is a function of the stress, rather than stress being a function of the strain. So this is sort of backwards mathematically, but in order to get things to look right, they did it this way. So you exert a stress on A. Okay? Well, it strains. The strain is this way. It bends, it deforms, it does whatever. As long as it comes back to what it was before, then the stress and strain are linearly proportional to each other. Okay? You can do that. The more stress you put, the more strain you get, the more change you get. But somewhere up here, you add too much stress, and as long as that's a straight line, you call that elastic behavior. Compress a little, you get a little change. Compress a little more, you get a little more change. Yeah. But at some point, you press a little more, give it more stress, and suddenly there's a huge amount of change. That's not going to come back from that. That's a plastic deformation. Okay? You keep doing that more and more, and ultimately it's going to rupture, break, crush, whatever. Other materials, B here, you exert a stress and it has greater amount of strain, but it seems to be all elastic, but it never reaches plastic. You exert more, it's going to rupture. Glass. At cool temperatures, it will have elastic activity. When the wind blows really hard, you hear those winds going. There could be some slight variation in the glass, and it goes back. But too much, too soon, especially very quick, it's going to fracture. Okay? It does not have plastic deformation at normal temperatures. Heat it up, however, and it does this kind of stuff. You've seen the glass blowers? That's always very hot stuff they're doing. They can shape it any way they want to. Okay? And that's when you get plastic deformation. But at normal temperatures of pressure, glass may give a little bit, but you do too much to it, it's going to fracture, rupture. So those are two, actually several responses. Elastic behavior, plastic behavior, and rupture or breaking from the pressure. And notice all these things could change the way any material would act to it. So let's get specifically to, and by the way, 19.1 was interpreting the Earth's surface, 19.2 was Earth's changing features. That's what we're doing now, stress and strain. So let's look at some of these they're sort of stresses and strains going together. Okay? Now, these are most obvious. Doesn't mean that's the only place they happen, but they're most obvious in sedimentary rocks. Because guess what sedimentary rocks are? Layer on layer on layer on layer, and doing whatever its formation and stuff like that. So, sedimentary rocks are typically, their normal presentation is layers. Fairly uniform horizontal, not necessarily uniform, but uniformly horizontal layers. Okay? Now, they originate from flat sediment deposits. They come out of those deposits in fairly flat layers. Layers are usually horizontal. Okay? Now, first type of stresses and strains we're going to look at are what we call folds or folding. And this is when you have that uneven distribution of pressure. You have pressure coming up from below and different pressures from above, and you can actually bend the layered bedrock. Okay? We'll see pictures of that. In fact, let's see if we got one here. Well, this is the illustration. It's not actually a picture. You have some type of pressure coming up here, not as much over here. Now, this is extreme here, and you bend the sedimentary rock. And usually the colors aren't that distinct either, but you will have the bending. Okay? It results from stress-produced plastic strain. Now, again, a lot of times we see plastic strain in rocks. That means it's usually going to be heated up. So this probably occurred pretty deep under the Earth's surface. So this is sort of like a, what were those two terms we had? N and X. I can't think of the term. It's not quite the same thing as that, but it is very similar. Something down there where it was pretty warm, and you got the pressure, and you got plastic strain. Widespread horizontal stress can produce domes or basins. Okay? Now, I'm not sure this is the best illustration, but I wouldn't be surprised. Have any of you ever been to Stone Mountain, Georgia? Okay. Stone Mountain is one huge piece of granite that's just sort of sitting there in the middle of something. The general idea is that you had some, and now that's an igneous rock, it's not sedimentary, but you had some pressures from underneath, and you had that igneous rock coming up, and later the stuff eroded away from around it. So that's almost what we call a dome. Okay? A basin, on the other hand, this is getting a little bit into the next chapter, but I grew up on a farm in Georgia, and I'm sure they must have them here too. But over there, a lot of the underlying stuff in Georgia, what they call the parent material, the underlying bedrock, is granite, which is hard. It's doesn't change a lot. It's pretty resistant to chemical change and physical change and other things. So it's just pretty stable. However, there would be pockets every now and then where there were deposits of things they called chalk. Okay? Chalk is very easily weathered chemically. Okay? A little bit of acid is going to dissolve away that chalk pretty strongly. Okay? Well, what happens is acid rain, carbonic acid, we'll talk about this in the next chapter, it eats away at that chalk, and it's a very mild form of limestone. It eats away and it settles. And that's what they made, what they call them grady ponds, swampy areas, low-lying areas. They were probably underlain by things, and that would be a basin. You know, in other words, the soil subsided underneath that. Now we have some other things that are producing some basins we really don't want to be happening, and yet they are. I heard this on the news last week or week before. What's the biggest agricultural state in the country? What produces the most agriculture? Huh?
Agriculture. State.
State.
Nebraska.
Say again? Okay, you would think something like that. It's actually California. California has huge areas, massive agriculture, almonds, pistachios, lettuce, tomato, raisins, grapes, I mean, just huge amounts of agriculture. Huh? And it's a huge state, too. Huh? Okay, we aren't going there. Okay. Okay. All right. Now, you name some of these others, like Alabama, where we get plenty of rainfall, and Nebraska gets a fair amount. Guess what? California doesn't. So what do? They irrigate like crazy. Okay? And in irrigating like crazy, they like to use the water coming off the Sierra Nevadas and the Rockies, coming down like that. They like to pipe in water from other places, draining rivers and lakes somewhere else. They think they deserve it all. And when they can't get enough of that, they start drilling wells. Now, they also do this in West Texas because it's very dry out there, too. They drilled and drilled and drilled, and they're going deeper and deeper, taking the water out. And guess what? The water, we'll talk about this in later chapter 2, the water is part of the water table. It fills the pores between the soil. And when they pump it out, the water table goes down. Now you have that pore space, and it collapses. Once it collapses, it's not going to recharge. You can't pump up and get space again. It's already collapsed. And they're doing that in California. They've already done it in West Texas. They have areas that have subsided, is what they call it. Those form basins. And there's no getting them back again. So even if they have a lot of rainy seasons, it's going to run off to something else. Some pretty stupid stuff we do. But economically, it's for the short run. Oh yeah, I can make money now, be care of what's going to happen in the future. All right, so let's go back. This is a picture of what they call an anticline, an arch-shaped structure that the pressure came from the middle and pushed it up, an anticline. Now, I remember that arch. I remember what an arch is. Anticline, they start with the same letter. Whereas the trough-type structure, like the Grady ponds or something, where the subsidence happens and it sinks down, that is called, then forms a trough-shaped structure, that's called the syncline. It's the one that doesn't start with A, the syncline, is the trough structure. So that's would be an example of an anticline. That would be a syncline. And that's the trough-shaped structure. Again, the younger strata actually sinks, whereas before it rose, the older gives way and goes deeper as well. So that would be a syncline. Now here, yuck. All right, I think we'll get here, but let's cover the words first, and then we'll look at pictures. So what folding is are bends in that layered bedrock. Especially if it's layered, it's usually sedimentary. And if you have bends in it, where it either comes up or goes down or whatever, that's what we call a fold. As the results of the stress produce plastic strain. It doesn't recover from this. It stays bent. Okay? Now, if the stresses are compressional stresses, the odds are it's going to be forcing it up into an arc, an anticline. If they're tensional forces, the odds are that's going to be dropping it, and that would be more of your synclines. Okay? So, and if it's transformed, you probably don't have either of those too much, maybe a little bit. Okay? That's mostly plastic strain. Remember, the plastic happens at higher temperatures usually too, so that may have been very deep when that happened. It may now be on the surface that it's been raised up later, but when the actual strain and folding happened was much, much earlier. Now, if there's widespread horizontal stress, that can produce the domes of it. This is the same thing we just looked at. However, you'll just see it shaped differently. Okay, so let's look at some of the pictures here. Now, what does this appear to be? What kind of rock? Sedimentary rock, and all of it is pretty much horizontal. There's been a lot of erosion. We'll cover that in the next chapter, but it's pretty much uniform sedimentary rock. However, that is not. It's still sedimentary rock because you can see the layers in it, but here you've had a stress under here, pushing up, maybe a different thing here. This would be a
That's a incline.
anticline. This would be a syncline. Okay, you got it. So that's folded rock. That didn't happen easily. That probably was very deep and probably pretty hot to get rock to fold like that. I can imagine the stress that would produce that if you didn't have a lot of heat. Now, you'll see something else here, and we'll talk about that later. Here we have a little, looks like a little crack or a crevice. That's the next thing we're going to do, okay? But before we go there, here's a much bigger shot, okay? Where is this? Let's see. It doesn't say here. It seems like in the old text that came from, that was somewhere in Montana or somewhere out west. It may have even been Canada, western Canada. Yeah. Look how much it was pushed up. These are vehicles here. There's a person. Look at that. This is a anticline and syncline. So differences in pressure must have been at very high temperatures. This was sedimentary rock. You can see the layers there, but they're no longer horizontal. They have been deformed big time. probably compressional stresses, I'm guessing, okay? And it must have been at pretty high temperatures. So if this is this far up now, it must have happened way, way deep, and things are continuing to push it up and eroding away. So that's pretty major. But again, you'll notice there are also some cracks and crevices here. Okay, we'll talk about those next. Okay.
So both of them reaction was going on at the same time.
What's that?
That anticline and the semicline was going on.
Yeah, and this is probably compressional forces forcing some down and some up. Yeah.
Usually they'll be together like that. And
Yeah,
when
they
the
can be.
incline, you'll see it.
They can be. Now, sometimes, like Stone Mountain is just a big dome. It's not got much of an syncline associated with it. Yeah.
So that's an example of what sedimentary rock looks like, and igneous rock would look like magma, or what lava would produce.
Right.
What would an example of metamorphic rock look
Okay.
like?
Maybe like hail and
What were you saying?
hail in the Cayman Islands.
Oh, okay. I'm not familiar with that. Okay.
Yeah. That's a type of
This could also be part of an answer to that. If you think about igneous rock, especially if it's formed from lava, that's in layers too. So not all layered rock is sedimentary. You can have igneous rock in some sort of layers too. But what I would suggest is some of the deep stuff under here, you may find out this is metamorphic because it's had all that pressure, and especially if it's down at heat, you may have sedimentary up here, but you may have marble down here, limestone up here, but marble somewhere way deeper. So it could still have been going through the same processes. So you can't just look at that and say, well, this you can't say, yeah, look at the layers here, that's obviously sedimentary, but if some of those layers have been modified, then it may actually be metamorphic, but it still has the layer because it came from sedimentary rock. So yeah, that's a good point. But that does look pretty classic sedimentary. Okay. Now, this would be more of a dome type structure. Okay. Again, the oldest formation is been exposed here because it's pushed up from underneath. This was not Stone Mountain. Stone Mountain didn't erode away. This did. So your layers on top, once it was forced up, it eroded away and ran off and stuff like this, with rain and stuff like this. But this is the oldest layers here. Newer layers are around there. Still sedimentary rock. Of course, Stone Mountain is more igneous. Okay? And it's pretty hard granite that doesn't erode away. But this sedimentary rock, especially, and we'll hit this a little later too, next chapter, when you start bending things upward, you got more pressure underneath, less on top, and yet you're stretching that surface, you're going to cause fracturing. And then when you got fracturing, then rain and wind and stuff can erode it more easily. So we'll see that in the next chapter, and that's exactly what happened here. And I think this may be Sundance Mountain. Is that in their text? I don't think it is. I think that was the old edition, and I'm pretty sure that I'm thinking this is Sundance Mountain, which I think of Cassie and Sundance Kids, and the Sundance Film Festival, that kind of stuff. So this is an example of a dome. Widespread horizontal stress could produce domes and basins. That was a dome, you just had a lot of it eroded away. You still have some doming here and some doming here, but a lot of it's been eroded away. And the sedimentary rock is very easily eroded, usually, because it may not have had all the compaction and cementation that it needed, and easily to erode, especially when you've had stressors underneath it that stretch that. All right. The next kind of result, you might say strain, that came from your stresses are your faults. Okay? The faulted or faulting. These are produced by relative movement on opposite sides of a crack. Okay? In other words, the folded mountains were mostly plastic results. That was your strain. The faults, you've actually had breakage. So you've actually had a fracture. Okay? So the fault, and then what you have is relative movement to opposite sides of a crack. Now, if you think back there, I said, look at the cracks and crevices there. There was so much stress after a while that it actually did. It was a fold and actually then later faulted as well. Okay? Now, we name these basically to foot walls and hanging walls. Okay? We'll talk about that and we'll show a picture of it later. What the foot wall is a mass of rock beneath the fault. The fault is the crack. Okay? So below it is the footwall. The part above the crack is the hanging wall. The mass of rock above the fault of the crack. The fault plane is that plane along that crack. It's the surface between the footwall and the hanging wall. Okay, now that we got the words in, let's see the pictures. Okay? Here is the crack. Now, usually they're not vertical nor horizontal. They're somewhat in between. So which of these would be the footwall and the hanging wall? One on the right, one on the left. Which is one? You probably can read it, but if you can't.
The left is the football.
One on the left. The right is the footwall. It's beneath the crack. Here's the crack below here. It's the footwall, even though it looks higher than the hanging wall.
Right.
Okay? So, yeah, that's the difference. What has happened here, the hanging wall has slid down the footwall. And by seeing that, you know this was a tensional stress. It was pulling apart, so one had to slide down. Okay? The hanging wall slid down the footwall. Okay? What's that?
What causes it to separate? Because
Right. Well, you have the stress, the tensional stress here. It could do a couple of things. It could fold into a syncline, or the rock may not. It may be brittle. It may be really hard, and it continues there until it finds a weak place, and then it cracks. So that's the fracture. Okay, and then the movement, the fault, it moves down down there. That is an illustration. Here is an actual picture. And it's pretty amazing how that usually does do a plane. A pretty flat, even, rather regular plane. And you can tell by the sediments here, this light, well, okay, which is foot, which is hanging.
The foot is on the right.
Foot is on the right and the hanging's on the left. But again, the hanging wall has slid down the footwall because this should be there, this should be there. It is slid down. Okay? Pretty obvious because of the coloration. And that happens with sedimentary rock. You have different colors and different types of things settle at different times. And then later when you have the folding or the faulting is actually the breakage. Okay? So that would be, and by the way, we'll get to that in a second. I was going to tell you what kind of fault that is. That's on the next slide. Are people still getting this, or are you doing something else? Do I move on? Huh? Go ahead. Okay. I can't tell when I see you writing. I don't know if you're writing this or writing something else. So we go into classifier faults now. Oh boy, you have a lot. No, I'm just kidding. Okay. Classes of faults. Two major kinds and one sort of sub-major. The first is your normal fault. That's where the hanging wall has moved down relative to the footwall. The last two we saw were normal faults. Now, don't worry about these too much. In case you run into the words anytime in the future, here's what's happening. And remember, your normal faults usually come with tensional stresses. You pull it apart, and the hanging wall slides down the footwall. Now, if you had a footwall over here and a footwall over here, and the hanging wall in between slid down both ways, then this produces what they call the blocks surrounded by normal faults drops down. Okay? So in other words, the hanging wall going down the footwall, in between two footwalls, that is called the gradient. It's dropped down. Okay? So that wouldn't be, it sort of looks like a syncline, but it's not, because it's actually along a fault, not a bend. Okay? The horse, on the other hand, and where these words come from, they sound very German to me, but too short for German. The block surrounding the normal faults is uplifted. In other words, here's your normal faults. On either side, your hanging walls have fallen down, leaving the part with the footwalls on either side elevated. That's called the horse. Okay? Kind of looks like the saddle of a horse. Okay, I don't know how to remember that. Don't worry about it. You don't have to memorize this. But notice here your stresses were tensional stresses on all these, because all of these are normal faults. The footwall has slid down. The hanging wall has slid down the footwall. Okay, everybody got it? Okay. The other faults is a reverse fault. That's when the hanging wall moves up relative to the footwall. How is that going to happen? Compressional stresses, because you have to push it up there. Normally it would slide down, yes.
Is that an example of subduction, where one plate goes underneath another?
Okay, that would be entire plates. These are rock, that had fractured. Those are plates that were separate to begin with, but it's a lot like that. You're right, but this is actually a rock that has undergone the stresses. These were compressional stresses, and they were pushing them together. Something had to give. Probably it was too cool to bend, so it actually broke. That was your fault, as opposed to a fold. And the faults, as they're pushed together, it pushes the hanging wall up that crack, that ring. And that's then called the reverse fault. Normally the hanging wall slides down, that's a normal fault. When it's pushed up, that's a reverse fault. Compressive stresses, whereas the normal faults are usually tensional stresses. Now, this is sort of the sublet. A thrust fault is a reverse fault, but it's a very low angle reverse fault. One like this would just be called a reverse fault. One like this would be called a thrust fault. Okay? Here are the pictures of those. This would be a normal, reverse fault, where the hanging wall now has been pushed up the footwall. That took compressional forces. Okay? Over here is a very slow angle. Still, it was pushed up at a very small angle. That's a thrust fault. Generally, you hardly detect. Here you see very definitely you have a faulting going on here. Here, it happens so gradually and slowly. Usually it wears down and you hardly notice any at all. You almost have to have the cutaway view to see there really was a fault there. This is pretty obvious, not something faulted there. Notice here in the reverse faults, you sort of get an overhang, whereas, going the wrong way. These, it's not an overhang, but you're going uphill, like you normally would. Not, you can climb this fairly easily, perhaps. At least you're going up, whereas the reverse faults, it's on top of you. That would be very difficult to go up. Okay, so that's why it's called reverse. How I think of it as reverse. Okay, so the faults themselves provide information on the stresses producing the formation. Certainly, if they're normal faults, that indicates that they're probably tensional forces. If they're reverse faults or thrust faults, that comes from compressional forces. So the faults do provide information on the stresses. Stresses are the forces. Okay? Make sense? Everybody got it? Okay. So that's that part. Okay? Now, your text has an illustration they don't have in the slides. Well, they have a couple of them. Okay. And they hardly look like some of these fit here. Some of them do, obviously, but some don't. Your figure 19.8 are columnar joining forms at right angle to the surface as basalt cools. Okay? That sentence doesn't tell me a lot. I know what it's talking about because I have a good idea. The sentence itself, I don't think describes it too well. But the picture on the left, A, is Devil's Post Pile. They put the devil in a lot of these things. I don't know. The San Joaquin River in California. Okay. The second one, the one on the right, is the Devil's Tower in Wyoming. And it's pretty much rises straight up. They're using another term there that, let's go back here, way at the beginning of faulting. Okay? And I'll point it out to you in the book as well. When they first mentioned faulting, this is on page 485. Okay? About middle way down that paragraph that starts under faulting, it says, if there is a breaking of the rock, that's the fault, well, okay, it could be, without relative displacement on either side of the break. You have a break, but there's no displacement. That's called a joint. Okay, now not like y'all were talking about. Okay, all right. I'm peanut gallery over here. Okay, okay. That's called a joint, and that's why they call jointing. Okay. If there is displacement, then it's a fault. Just having the crack there with no displacement, that's not a fault, it's a joint. It's a crack for sure, a fracture, but if there's been no relative motion, it's just a joint. If there has been relative motion, then it's a fault. Okay? So then when they're talking here in the picture, the columnar joining, those are joints, formed at right angles to the surface as the basalt cools. The cracks are there, but there's been no movement. So those are joints. Okay? Same thing with Devil's Tower. You see the cracks there, but there's no relative movement of them. Those are joints, not faults. Okay?
So do you think someone has...
What's that?
Do you think someone has climbed that mountain?
Okay, I'm
Do
sorry.
you think someone has gone up on top of that mountain without sliding through the joints?
Okay. I heard you something about the top of the mountain.
Yeah, do you think anyone has climbed?
Oh, it's flying. Okay. It is so interesting that you say that. Okay? Because part of the lab for this chapter is going to be, or it's either this chapter or a later chapter, it's going to be talking about Devil's Tower. It's going to be talking about, a lot of things about it. And the last question is it too steep to hike? And you'll see when you look into that, you'll find out yeah or no. So I don't want to answer that now because that's going to come up on us. But when I look at that, I say there ain't no way. Okay, but I'm not sure that there's not. I bet you a good mountain climber could do it, especially on those sides that you have a little more slope. But some of the people want to go straight up the vertical side. So I don't want to say you can't do it. I'll say I can't do it. Okay? And I ain't about to try to do it. Okay. Okay. There's another picture, and this is something I found sort of interesting. The relationship between the hanging wall and the hanging wall block and the footwall block at fault. For the life of me, I can't make out a lot of sense in the A part there. The photo of a fault. Now, the second part, yeah, that makes sense. Kingman, Arizona, showing how the hanging wall has moved relative to the footwall. And that one's really hard to tell which is which because it's almost vertical, okay? It actually seems to be tilting a little bit on the bottom and different on the top, but that place where it does slant, that gives it away, okay? And the hanging wall has fallen down. But boy, that upper one, the A part on figure 19.9, the relationship between hanging wall block and footwall block of a fault. It's just illustrating that. I do not know why they have a man in a device in there. I guess they're showing that you're doing mining there, but that looks so artificial. I mean, it's just not even true. And they talk about the ore vein along the fault, which I guess that's where you find ores. That top part, I think, leaves a lot to be desired. Okay. So we've done those. We've classified. Okay. Now we're ready for the next, and there is an example here, example 19.1. A graben is bounded on the east and west by two normal faults. The fault plane, and it does slopes and things like this. And since we haven't done those, you don't have to do them, but they still may be interesting to read through and see what they're talking about. Okay. Then 19.3 is earthquakes. Okay? What is an earthquake? That's pretty much what it says. A quaking, shaking, vibrating, sometimes upheaval of the ground. There usually isn't too much upheaval. There can be, but not much. It's just the shaking, quaking, vibrating. The science fiction, where the earth opens up and people fall in, that's fiction. Okay? It doesn't happen that way. Okay? Yes.
But oftentimes when sometimes you see on the news how, in a way, the road or the ground opens up and cars tend to fall into a ditch. I get what you're saying. People don't fall into oblivion. There's just like this big hole that's left because of an earthquake or even like what do you call it?
Sinkhole. Okay. Well, when you see cars falling off something, usually that's a rigid man-made structure like a bridge or an overpass. And then you have the earthquake, it weakens that, and something does fall because it's already elevated. You weaken the structure and something falls. That, yes, happens. But that's usually man-made. The ground itself doesn't fall apart and suddenly there's an abyss here that you go down and where's the bottom? We don't know. That doesn't happen often now. Ice fields, glaciers, yeah, you have some of those kind of things. But that's a whole different thing. You've got moving water. Some moves and some doesn't. You have a big fissure in between. But generally the ground doesn't do that. Okay? Man-made structures do that, because they're fixed. This one's fixed in place. This one's not fixed as well. Yeah, it falls off. But the movies where the ground opens up and people are falling into the hole, that's not typical. What's that?
So the movie San Andreas?
Yeah.
It will be.
What movie was that?
San Andreas?
Say it again.
San Andreas.
San Andreas.
Yes, that's
They
the
named that.
movie. Yes. It's
Yeah.
movie.
Yeah, I bet you it's mostly more fiction than science.
Well, it's more science.
Oh, good.
Yeah, it's pretty good.
Good deal.
So you know a lot of.
Well,
Yeah. The theory is science, but
yeah.
It's moving.
It's moving.
Now, why do earthquakes occur? Result from sudden release of energy from stress on rocks. So, let's say we have one of those transform boundaries, the shear stresses going this way. There's some rock sticking out there that's holding that up, keeping the motion from happening that needs to be and wants to be happening. And it's there, and when suddenly, say, the rock fractures or gives, then you have the sudden quake. That's what the earthquake is, okay? And you definitely have movement, but it's not this kind of movement. This kind of movement does happen in the mid-Atlantic ridge. But guess what? Where it moves apart, here comes lava bubbling up there. So it's not a big abyss. It opens up, and here comes new lava coming up out of the middle. So very different, okay? Very different. The vibrations that are produced from that shaking, those are your seismic waves. And we've already talked about there's three types of seismic waves. Remember what they are? P waves, which means primary are pressure waves, okay, which also are called longitudinal waves. Okay, the second was secondary waves, S waves, which are also, they're a little bit slower, they're shear waves. The motion is like this, but the direction is like that. Okay? And a longitudinal wave, the motion is like this and the transmission is like that. Okay? And then what was the third? Yeah, and that's called surface waves. That after it reaches the surface, what dissipates there are surface waves. So those are your three types of seismic waves. Most occur along the fault planes. Most earthquakes occur along fault planes when one's trying to move, it got held up, and then finally gives with sort of a major vibration when one side is displaced with respect to the other. That could be tensional, tensional, it could be compressional, or it could be shear. Okay? But you have motion. Something was holding up the motion, suddenly gave. That's what produces the earthquake. So what are the causes? Well, let's go back to our elastic plastic type thing. Usually plastic deformation, which is usually your folding, happens at higher temperatures when the rock's a little softer and can bend and deform like that. But this is elastic. So either that rock pressure, and then it gave and bounced back to where its original shape was, that would be the elastic rebound theory. Two plates are tightly together, pressed tightly together, friction restricts the motion, and it could be this kind of motion, any kind of motion, and the stress builds up until the friction or the rock rupture strength is overcome. One or the other, either the rock breaks or the friction overcomes. It's sort of like this on the friction part. I can push on this desk and nothing much happens. But if I keep pushing, all of a sudden things fall around. Well, that's because static friction is stronger than kinetic friction. Okay? And so static friction you keep there until finally it gives, and then because kinetic friction is less, it goes more quickly. So that would create a situation in which an earthquake is static friction. When finally it releases, that results in the motion. Okay? So either the friction is overcome or the rock ruptures and overcomes. The stressed rock snaps suddenly into a new position. That would be elastic rebound, or it fractures and just gives way. Now, one of these faults, and this is basically a stress fault, is the San Andreas fault. And you mentioned the movie too. Look where it goes right through the middle of San Francisco. In fact, I wouldn't be surprised if San Francisco Bay is not there because of some really major also, if you go down here, this is San Diego down here. This is Mexico beneath that. Tijuana somewhere right in there. If you go on down there, south of there, and this is just my idea. I've never seen it before, but just by the pictures they have.
Glow, baby.
What's that?
It's in glow.
Yeah, get the glow. Okay. If you extend this picture on down here, you see how it goes inland for a little ways? What you run into? The Gulf of California. There's the Baja Peninsula there. And I think that's got to lie right along that fault. I wouldn't be at all surprised if that's part of that fault. I don't know that for a fact. It just seems reasonable to me by where it's located that it has done a major thing there. Just for instance, this is a completely different kind. This is from plate movement. The Red Sea here, famous biblically, that is the result of plate tectonics. This is the Arabian plate. This is the African plate. It's a big rift between the two right there. Okay, it goes on up, and that's where the Suez Canal is right in there. Okay, connecting those. What's that?
I was just wondering.
Well, I couldn't hear what you said there.
When you see it in the fault line runs right through the Red Sea,
Yeah.
Well,
Well, yeah, with the Suez Canal being right there, it's a pretty major construction right on the fault line. Okay, it may work for centuries or decades, but at some point there may be a pretty major eruption there, and all that is pretty much destroyed, So, yeah. Well, I mean, here we have a city right on top of this fault line, San Francisco. And Los Angeles, there's a city along here. Los Angeles spreads like crazy. It may not be called Los Angeles, but it's something else from there. So yeah, all these things are pretty close to that. There's lots of communities, and we're going to see a picture in just a short time. Somewhere in this area, somewhere here, of a field, and it's just amazing. It's in your book. I hope it's on the slides here. Okay, so that's one of the major fault lines in the U.S., San Andreas Fault. While we're here, let me just point something else out to you. We think of all this happening, kind of the ring of fire type thing, where subduction and stuff like that's going on. That's where your volcanic action is, your earthquakes and all like that are there. But that's not the only place. A fairly interior state, Missouri, has another fault line in it. And that's right in the middle of the North Atlantic plate. And yet there's a fault line there. And that's called, and this is on the right-hand thing of side of your page 288. Most earthquakes are explained by movements of rock blocks along faults, but there are also other causes. Earthquakes have occurred in the eastern U.S. without apparent relationship to known faults and other or near the surface. One of the largest earthquakes on record in the U.S. occurred not in California, but in a region near of New Madrid, Missouri. Now, we pronounce it Madrid, but I think that's called Madrid, because Missourians don't know how to talk about it. I'm sorry, I didn't say that. In 1811, the quake toppled chimneys 400 miles away in Ohio. It was felt in the Rocky Mountains to the Atlantic coast, from Canada to the Gulf of Mexico. The New Madrid fault zone was theorized to represent a failed rift that is being reactivated by compressional stresses east to west. So there's still stresses within a plate, And if there are any weaknesses there, you can have breakage there too. Now, I'm pretty sure that was the one. I don't think they mention it here.
Did they say what that earthquake measured?
I don't know. They didn't have the Richter scale in 1811, but it was pretty powerful. It was so powerful. Now, Missouri, borders the Mississippi, right? They said the Mississippi River, a portion of the Mississippi River, ran backwards for a few days because it was that major. And the water went that way, and then later it started going back downstream again. So it was major. I'm pretty sure that was documented. They don't say that here, but I've read that elsewhere. Amazing. Okay. Now, here's the picture I find just fascinating. Like I said, California is a very agricultural state. Anyone want to get an idea where the fault line is? San Andreas Fault? There it is. Right down the middle of that field. Okay? And see, that's a transform boundary, a shear stress. When the farmer plowed this and planted it, these were straight. Then the earthquake hit. And look how, boy, can you imagine cultivating that field later? It's harvesting it. That's going to be a fun time. This is a rather bizarre illustration up here. It is showing what's going on. You have the shear forces. Those are going in opposite directions there. And never do you see fence lines bend and roads bend like that. That just doesn't happen. This is sort of what you're talking about. That's a man-made structure. It's going to fracture. It's not going to bend. But if the stresses get so straight, because it's so great, something gives, and then it releases. And again, I don't think there are any earthquakes that would displace, what is that? About 18 feet or something like that. Not a whole road width, nothing. But the earthquake was down here. Hard to say here where we'll talk about that in a slide or two, but you can see you have a shear stresses there. A transform boundary. Okay. That to me is one of the neatest pictures. Okay, how do we locate and measure earthquakes? Two terms here we probably get really screwed up. You always hear people talk about the epicenter of the earthquake, and that sounds like that's where it occurred. That was the center of it. That's not the center. It occurred at the focus of the earthquake. You never hear, or hardly ever hear, anyone talk about the focus of the earthquake. The actual origin of the earthquake, wherever that rock gave way, or whatever it was that gave way down there, that's the origin. Way deep, somewhere down there. Now, what the epicenter is, and this is what everyone talks about, that's the location on the Earth's surface directly above that focus. That's the epicenter. Okay? So the focus is where it actually occurred. The epicenter is on the surface of the Earth above the focus, because that's what we measure everything from. How far are you from it? Well, it may have been a mile or so down. So yeah, I was right above it, but it was a mile from it. No, you say I was right on the epicenter. Okay. Now, a seismograph is something that measures, that's graph, actually draws the seismic waves. That's what a seismograph is. The instrument used to detect and measure earthquakes. Okay. It detects three types of waves. Remember we talked about these? The P waves, primary waves, pressure waves, the fastest of the waves. These are also longitudinal waves. The S waves are the secondary waves, the shear waves, the transverse wave. The motion is up and down, but the wave is perpendicular to it. The P wave, the motion is in the direction of the transmission. And then the surface wave, which is just up and down once the seismic wave has reached the surface of the Earth and then spreads out. That's the surface wave. And it's just sort of up and down motion. Okay? These are the fastest the seismograph detects them first. Later comes the S waves. They're a little bit slower, but then it measures those. The surface waves, because the seismograph's actually on the surface, that's usually the biggest wave, but it comes later. Okay? That does the most shaking of the machine. Well, here's the picture that shows this. The break actually occurred there. The give way was right there. That's the focus. The waves go out three-dimensionally, radially from that, the seismic waves. Directly above this, even though the fault line's way over here, the epicenter is here because what kind of fault is that? What kind of fault would that be? What? There is a fault plane right there, but what kind of fault is it?
Reverse.
Say again?
Reverse fault.
Okay.
Reverse fault.
No, the reverse fault, the hanging wall would be pushed up the footwall. Here's the footwall, here's the hanging wall, it fell down. That's the normal place where it goes downhill. So that's the normal fault. Okay? But it got hung up right there, and when it finally gave, that was an earthquake. So even though the fault plane's over here, the epicenter's there. It's always, most of the time, associated with a fault plane, but you would think, oh, that's a good deal from it. Well, it's directly over it, way down deep. Okay. Here is a picture or illustration of a seismograph. Now, what you have, this is firmly, totally grounded in the bedrock. Okay? That is part of it. Okay? That is too. All this is together. But you have freedom of motion of this thing. This is hanging from a wire, and it has a swivel type thing here. And when you have ground movement, then that thing moves. It's going along most of the time. You always have a little bit of what they call noise, just a little bit of thing. But then all of a sudden, when you see a major change happen, that was your P wave, your primary wave. You'll see another major change happen, that's your secondary wave. And then when you start feeling it, that's your surface waves. And those are usually even bigger. Okay? But here's a heavy weight whose inertia keeps that from moving too rapidly, but keeps it pretty much, make sure that you're recording what you're sensing. Okay? So, the seismic data we collect, the P waves travel faster than the S waves. Primary travels faster than secondary. Pressure waves travel faster than shear waves. Okay? Longitudinal waves travel faster than the transverse waves. Any way you want to say that. Okay? The difference in the arrival time, since these travel faster than those, the difference in the arrival times correlates to how far you are from the earthquake. If you get the P waves and then just within a few minutes get the S waves, you're pretty close to that thing because it didn't have much time for them to get far apart. But if you get the P waves many minutes ahead of the S waves, you're much further from that epicenter. Okay? And those as well. So that difference in the arrival time correlates to how far you are from the earthquake. What they do is triangulation. Now remember, I think I said this before, two major areas where scientists from every country on the earth, North Korea, you'd hope all of them, participate very nicely with seismic data and tsunami data. Of course, a landlocked country won't worry about tsunami. It's all over the sea. But every country has seismic, and they all are calibrated and kept up. So what they have these stations all over the place. So if the stations, there's not one in Birmingham, but let's just say there was one here in Bessemer, Alabama, and you got a certain difference in time between your P wave and S wave here. You do that on a table and find out you're 300 miles from that epicenter. say, Mexico City also has one, and they have their distance, whatever it turns out to be. And then say Brazil has one, where you get 3 different sites, and you know about how far you were from the center, so you draw a circle here, a circle there, a circle there, where they intersect. You get the place. Can you do it with 2? No. Here's the example. Okay. Now here's what you get. This is your distance from the earthquake. The further you are from the earthquake, the greater the distance between the P waves and S waves. So this is time of first arrival. P waves always get there first, but if you're really close to it, there's a very short time distance between those two. If you're further away, then it's a wider time. It just keeps getting wider. Okay? So you measure the time difference between the P waves and S waves. You enter this table, and that tells you about how far you are from the earthquake. So say we were 200 kilometers away. We draw a circle here. Okay? Venezuela, say. They draw a circle there. Well, these 2 circles actually intersect in 2 places. So the epicenter is either here or there, but we don't know which. So when we get a 3rd circle that intersects a couple of other places, that one, that's the one where it is. So you have to have 3. That's why triangularization is important. Guess what? Same thing that works with your GPS. You have to have a signal. You don't realize this. You have to have a signal from at least 3 satellites, 3 different satellites. Otherwise, you don't know where you are. You don't have a clue. And the computer, nothing has a clue unless you have 3 signals. Okay. Quite often you have more than 3, and that just helps confirm that's where the signal was. Okay. Does that make sense? Now, how do we classify? We always like to classify, don't we? How do we classify earthquakes? 3 classifications. The first is what they call shallow focus earthquakes. What's the focus? Where it actually occurred, somewhere down deep. Okay? Now, what do we mean by shallow focus? If that focus is 70 kilometers deep, that is about 42 miles deep. Do I count that shallow? No, that sounds pretty deep to me. So, but 42 miles deep, 70 kilometers deep, that's the shallow. Anything between the surface and 42 miles down. 85% of all earthquakes occur in the shallow focus. Because guess what? Near the surface, within 42 miles of the surface, the rocks are more brittle. They'll tend, if they hang up, then they break. You get more plate friction near the surface. Down further, where it's a little bit softer rock because it's hot, it slides past each other better, not on the surface. So 85% of all earthquakes is within the top 42 miles of the thing. That's mostly in the Earth's crust. Okay? Now, the intermediate focus earthquakes are from 42 miles to 180 miles deep. That's intermediate. Okay? Now you're into the upper part of the mantle. Okay? You're still in. Okay. The mantle is really thick. You're still in just the very upper part of that. Okay? The deep focus earthquakes are from, and they got something wrong here. I'm pretty sure that's supposed to be 350. Every time I see this, I know it's wrong, but I never remember which exactly it is. Yeah, here we go. That should be 70 to 350. Okay, let me get my pen activated here. Well, let's do it in blue. This should be 350 kilometers. So I was wrong on the 180. That would be closer to 200, 200 some odd miles, around 200 miles. Okay. Upper part of the mantle. Actually, the upper part of the upper mantle. Okay. The deep focus earthquakes, the really, really deep ones, go from 350 kilometers, which is, let's say, about 200 miles, down to 420 miles deep. Now you're in the lower part of the upper mantle. Okay? Lower part of the upper mantle. Why are you not in the lower mantle? Anyone think of a reason you wouldn't be in the lower mantle? What's in between the lower mantle and upper mantle? The what? Okay, yeah, you're getting too hot, but that is the asthenosphere. All the plate movement and everything else is above the asthenosphere. So that's why you have to be in the upper mantle, the part of the mantle above the asthenosphere. And it's not the upper part of that, that's the intermediate quake. It's the lower part of the upper mantle, above the asthenosphere. Okay. Now this is about 3% of all earthquakes. Not very many do we measure way down there. The rock is too hot and plastic that it just doesn't give much. But how many would be here in the intermediate focus? 85% in the shallow focus, 3% in deep focus. What's left? Second? 12%. 12% would be here. Why they didn't list it, I don't know. So most of them, vast majority, are shallow focus, which can be as much as 40 miles down. You know, that's still shallow. But if anything between 42 and say 200 miles, that's intermediate, and then between 200 and 420 miles, that's deep, really deep. Okay, that's where the focus is, beneath the epicenter. Now, I wish that we had a slide of figure 1915. This is really one of the neatest slides, neatest figures, and they don't have a slide on it. This actually shows the P waves are just a little red line that goes like this. Okay? The S waves are the wavy line on top of that. The surface waves are the ones that go like that. The P waves get there first, highest velocity waves. The S waves get there a little bit later. There's the slower waves. And then the surface waves, they are pretty slow. Here's how they look on the seismograph. Say that one that was relatively close, you get an intense P wave, and then it almost goes back to normal, and then you get an S wave, and it almost goes back to normal, and then you get the surface waves that really irritate it. It'll be a while before they zoom out. A little bit further away, you didn't get anything there for the longest time, but then you get the P waves, then you get the S waves, then you get the surface waves, and again, it's the time lag between P and S. See, that's a short time lag, that's a longer time lag, which means you're much further from the earthquake. Okay? They have these stations all over the world. And I bet you sometimes North Korea is not too fond of us having all those, because we know every time they do a nuclear test, or anybody does a nuclear test, because those act like minor earthquakes. You can tell them on that. And you can pretty much pinpoint where it was. So when North Korea said they successfully tested a hydrogen bomb, there's sort of a lot of doubt about that, because that would have been a really big, because those are much more powerful than a fission bomb, and it just didn't seem like it happened. But who knows? All right. I think the example 19.3, we usually don't do many examples, but this one is worth doing. Which station is closer to the epicenter if one seismic station in Nevada receives the P waves at 4:30:15 p.m. and the S waves at 4:35 a.m.? So guess what? 20 seconds difference. Okay? While a different seismic station in California receives the P waves at 4:29:59 a.m., the S waves at 4:30:15 a.m. So what's the difference there? This is example 19.3 on page 491. Any ideas?
About 45 seconds.
Second?
About 45 seconds.
Which one?
I'm on the second California P wave at 4:29:59 a.m. and S wave at 4:30:15 a.m.
Yeah? And how much time you say the delay was?
I don't know. It wasn't even that. That was about 15 seconds.
Okay. It was 16 seconds. Okay. What was it for Nevada? That was 20 seconds. So sure, the California is a little bit closer. The other thing that gives that away, California got their first P wave a little bit ahead of the Nevada. So you figure it had to be closer. Okay. So yeah. All right. And the next one is just playing around with time, so I don't see, I mean, you could do it, but I don't see any new science in that. So that 19.3 did have, I think, good illustration. Okay, now we're talking about measuring earthquake strength. Okay, and there have been several devices or structures to try to do that. Originally, they measured an earthquake strength by its effects. Structural damage to buildings, fires, landslides, displacement of land surfaces, okay, tsunami, tidal waves. Okay, that's certainly a measure. Is that necessarily the best measure? Probably not. I don't know if you recall, I don't remember what year it was. Sometime in the last, I would say 5 to 6 years, I'm guessing that. Right around Christmas, I think it was maybe December 26th, there was a major earthquake in Haiti. Okay? I mean, say again? When was that? 2010. 2010. So 7 years ago. Or not quite 7. Okay? Because it was December 26th or something. I mean, the damage was massive. Hardly any buildings in Port-au-Prince were undamaged. Most of the structures were completely wiped out. Okay? I think it was maybe less than a month, certainly less than 2 months later, there was another earthquake in Chile, South America. And the structural damage was way, way less. Which was the strongest quake? Actually, the one in Chile. That doesn't seem to make sense. Except that Chile had so many quakes over the years. Chile is a pretty progressive country, one of the more, maybe a little bit more affluent in South America than most. They had very strong building codes to prevent earthquakes, a lot like California has. Boy, nowadays, if you're building something in California, roads and things like that, you have a lot more to do than building a bridge in Georgia or Alabama, because we don't usually have very many. California, they make you build them very, very strong. Well, that happened in Chile. Haiti, very poor country, very lenient, if any, building codes. People just threw up any kind of structures they wanted to. Most of their buildings were concrete block, which is just not that strong. Okay, in Chile, reinforced steel. Okay, strong, earthquake resistant. So you can't measure by the amount of structural damage because building codes may be so very, very different. But that was originally how. The San Francisco quake around the turn of the 20th century, the real big one that hit, that was when most of the buildings were wood structures. They were thrown up real fast. That was shortly, not that long after the gold rush, and it had just been a boom town. People just built fast and furious, but not very carefully. Major, major damage. The one that happened during the World Series, can't remember what year that was, probably was a stronger quake than the one that destroyed the city. But the building codes were much stronger then. So you can't always, I don't know what the relative sizes of those were. Okay, let's see. Beat it in just under the wire. Okay. This is Tierra, right? And Trey, I'm trying to find you. There you are. Trey. Okay, so we're only missing Jarrell, Cece. I knew was going to be missing Sean and Kedrick, but we're also missing because Chelsea had to leave. All right, we're talking about earthquakes, measuring earthquake strength on page 491. What's that? I can't hear. 333. Yeah. I don't call roll again until 3:45. I'll hit it then. And then we go until 5:15 for the test, chapter 18. Did either any of you came in, did you get the lab from before? Did you need it also? Huh? Oh, and you do too? Okay. I'm sorry, I forgot. Whoever else came in. There's two. Oh, come on now. Is that 2 or 3? 2. Okay. You needed a lab from, and you needed one too? Where? From Thursday.
We took the test also.
Huh?
Yeah, the test Thursday too.
Did we? Yeah, okay, well, we'll get that at the end. I've got to find out where my labs are. Those are which? Is that density of igneous rock? Okay. Where are they? Oh, I hear it. Why do I not have enough labs? Did someone get more than one? No, you need it. Okay. I'm going to have to make some more. I don't know where they are.
Actually, she like bread. Actually, she got a little
Okay. I don't know. I sat down that I needed 20 and I didn't get 20. So when I take a break, did anyone else not yet? The last lap. Everybody got it except Ashley, right? Okay. 1, 2, 3.
Did you say we can take a break?
What's that?
He said take a break.
Oh, you want to take a break?
Yes.
Okay. All right. I'll run down and make copies while y'all are breaking.
You're just awesome.
And it's time to call roll again, too. So I should have waited. Then, well, no, I think a few of you have come in since I made the first announcement. So several of you have heard this several times now, but let me say it one more time. The Vice President sent a memorandum late last week that all students who have not completed payment of their tuitions and fees and all other things, that if they have not gotten those complete by tomorrow, they were going to be removed from the roll. Now, just about everybody in the room has gotten theirs done, but not everybody. There were 3 that hadn't when I checked on Friday. I don't know if you have it now or not, but you need to get that done today or tomorrow. Or if you know you can't, but it's in the works, please contact someone in the business office. That would be our cashier's window, or if you're on the Birmingham campus upstairs on the A building, in the business office, and let them know what your situation is, so they might be able to put a flag on yours to keep you from getting removed from the class. But otherwise, they are going to remove all unpaid students. Tomorrow, I think, is in the business time, 5 o'clock this year. Okay. Now, for those who came in and just got your labs, let me mention this about the lab. If you notice, that lab is very short. The last page has 6 blanks on it for you to fill in masses, volumes, and densities of basalts and granite. We did that in the lab, so you should be able to hear it on the YouTube video. Okay, the one that we did last Thursday. It should be out there, and you should be able to hear it. Yes. What's that? See on the last page, very last page. You see those 6 blanks there? You can hear those on the YouTube video. And then you open it up and you'll see 4 questions on the inside. I think you can hear most of 3 of those questions on the YouTube videos as well. If you can't hear them all, get with one of your neighbors or friends or something that was there and see if you can pick up from them. But that gives you only 10 points worth. The lab is worth 25 points. Where do you get your next 15 points? From the questions at the end of the chapter, the ones that are named, questions for thought, and for further analysis. If you got the new book, that's on page 478. At the end of chapter 18, questions for thought, there's 16 of those, 4 for further analysis. That gives you a total of 20. You pick any 15 or more of those questions. The reason I say or more, in case you miss some, if you do a couple extra, you'll be more likely to get your full 25 points. Okay? If you just do 15 and miss some, then you may only get 24, 23, whatever. Okay, so I say do 25 or more. Now, when I passed these out to you last Thursday, I recommended you try to get those questions done by today when we have the test on that chapter. Now, those who just got your labs today, unless you listened to that over the weekend, you probably didn't hear that. So if you want not to take your test today at the last 30 minutes, but you'll need to make it up sometime during my office hours. And remember, I don't have many office hours, so you'll have to make it up. But if you want to wait until you get those questions done, you can do that, because I told everybody that. Okay. I think that covers everything. What's that? Mexico. 7.1. Okay, we haven't talked about that yet, so we will. Now, there was an earthquake just a day or so ago. I'm trying to remember where that was. It seemed like that was California. These are the aftershocks today, or?
Oh, no, I was just having an hour.
Yeah, it just happened an hour ago.
Just an hour.
Yeah.
An hour.
How
Yeah.
long does it take for the aftershock?
It can vary, but it's usually fairly close, like within a day or so.
Oh, okay.
All right. So we talked about that effects of the structural damage, not the best way to measure the strength of an earthquake. How much damage was done, but it's not the strength of the earthquake. A guy named Mercalli, and by the way, if someone hasn't chosen a paper topic yet, who was Mercalli? Or how did he develop the scale? Or tell me something about the Mercalli scale, okay? That would be a reasonable paper topic. Several of those would be reasonable paper topics. He talked about relative intensity, and he split it up into 12 categories. One was not felt at all. You sensed it on the seismograph, but no one felt it anywhere. That's the mildest of the quakes. Up to 12, total destruction with visible ground waves. You see the ground waves moving, okay? Now that's, again, somewhat subjective. Total destruction, visible ground waves. I need to go to the next slide before we go this, so we'll come back to that. Oh, no, I didn't, okay. That's all it says about Mercalli scale. In your book, it says a little bit more. No, let me do that. Okay. Now, this is way too much to put on a slide, but they did it anyway. But if you're looking in your book, on page 492, it's at the top of that page. But before we do that, at the bottom of 491, do earthquakes swallow people? In Hollywood, yes. In real life, no. Okay? So I'll let you look at that. Myths, mistakes, and misunderstanding. Okay, the earthquake safety. This is a closer look, top of page 492. Now you're going to see something very similar to this in just another couple chapters. Okay? Where we do weather. Very similar to what happens after a tornado or something like that. These, you'll see how similar these are. Okay? Well, there's some major differences too. Okay. Earthquake safety rules from the National Oceanic and Atmospheric Administration. Its short name is NOAA, NOAA. So if you ever hear James Finn, NOAA satellite, or NOAA this and that, it's not saying the old guy on the ark. I mean, on the not that NOAA. This is National Oceanic and Oceanic and Atmospheric Administration. Okay, during the shaking, it's not going to help at all to panic. So don't start running or rushing, falling downstairs, doing something silly like that. Do not panic. Okay? It's hard to say. I mean, easy to say, hard to do. If you're indoors, go and stay in there. Okay? Because the odds are, if it hasn't fallen on you by the time you feel it, probably not. Okay? But seek protection under a table, a desk, doorway, because you see doorways are pretty strong. So right under the doorway is probably safer. Okay? Stay away from glass. Again, if it's happening, you don't have much choice, but get away from glass if possible. And this was something, I mean, I'm sure they learned it in lots of places. The San Francisco quake, remember the one I was talking about at the turn of the 20th century, you know? More damage was done by the fire after the quake than was done by the quake. And the reason was they had natural gas lines running all over under the streets and stuff like this. They ruptured and people had things that they were, you know, if fires were breaking out or they were lighting or, you know, something else, it just caused enormous amount of things. Do not use matches, candles, even if you're in the dark. Don't strike a match. Let's see where I am. Well, I'm not there anymore. Okay. Yeah. Okay. Don't use any open flame. Okay. If you have fires, get rid of them. Okay. Get the fire extinguisher. Douse the flames because natural gas lines may be broken. You don't want them exploding on you. Okay. Don't panic. think of what you need to do. If you're outside, move away from the building, okay? Move away from power lines, okay? Stay in the open, okay? Not much is going to follow you if you're in the middle of the field, okay? Do not run through or near buildings, okay? Just not a good idea, like in between two buildings. This has nothing to do with earthquakes, but it has the same kind of idea. When I was the summer after my freshman year of college, no, yeah, summer after my freshman year of college. What did he say about how long that was ago? Okay, I was in the Navy ROTC, so that I was on what they call a third class midshipman cruise. I was on an old LSD, that's a landing ship's dock. Ship in the Navy. Okay. You're a lot like my dad. He got such a kick all summer long. People say, well, where's Charles this summer? He said, oh, he's on an LSD trip. Yeah. And, especially the pastor of the church, and things like that. He really got a kick out of doing that. Okay. But I was on that, and I was on my way back across the Atlantic. I'd been away for 6 weeks. Been the farthest I'd ever been from home. One of the longest time separations. I wasn't homesick or anything, but I was really looking forward to seeing my family. Okay? And they were going to come up and meet me when we pulled into Little Creek, Virginia, and I go from there. Well, we got pulled into port, and lots of people's families were there and stuff, and I was standing around waiting and looking, no family in sight. Of course, you're out at sea, you don't get mail, but the last mail I had gotten said they were planning to be there. So, nothing. So when finally they hooked up phone lines and stuff, I called the aunt that lived there. She said, oh, they've been trying to get in touch with you. Your brother was in an accident and they're having to stay home. What had happened, my older brother was going on his first class midshipman cruise at the same time. I was already out, and they were taking him. Well, my older brother and my younger brother got into some sort of spat, and they were hacked off at each other and stuff. And Dan decided he wasn't going to go see Mike off, so he was going to go spend the night with a friend. So he did. So my parents were out of town taking Mike to wherever it was that they had to catch the plane to go. And Dan stayed in town with a friend, and they were out just riding around, and they heard the fire trucks, the alarms and stuff going off. So, of course, let's follow the fire truck, see where the fire is, So they did. They shouldn't have, but they did. And there was a bunch of old houses, most of them abandoned, but very tinderbox-like houses that just were going up very fast. And they were pretty close together. And about 3 houses down, there was one that was actually occupied. So Dan and Jim Davidson, who he was spending the night with, decided to help those people get the furniture out of the house in case the fire made its way to theirs. So they were doing something good, okay, and they were helping move furniture out of the houses. And finally, the fire department, the volunteer fire department, got there and pretty much put out the fires. There was this one guy, and I knew him in high school. He wasn't the quickest horse in the race, we'll put it that way. And he decided the fires were out and stuff. He still had a hose, so he thought, let me spray this chimney, which was really hot because the house had just burned down, and watch the steam come off of it. Okay? So he was doing that, and Dan and Jim were helping the people get the furniture back in the house right next door. So he went between the houses, taking the furniture back in, or was on his way back to get the next piece, and this guy was spraying the chimney. The fire had damaged the chimney, weakened it, and the chimney fell over on top of my younger brother. And where the sides of the hot side of the brick hit him, 3rd-degree burns on about 6 pretty big places. Fortunately, mostly his legs and lower part. And of course, bricks hit him in the head and it knocked him out. And so he was under a pile of rubble, but he was going in between. So what I'm saying is, when there's things that could go wrong between buildings is not a good place to be. Now that was all the fault of the other guy who should have known better. He was on the volunteer fire department, but he did. Well, anyway, that's why my parents weren't there, because they were home nursing my brother, and he did well. But anyway, it was, don't go through or near buildings. If you're outside, stay outside. If you're inside, don't try to get out, because more than likely, if something's going to be falling, it's going to be falling out. Okay? If you're safe inside, stay inside. If you're in a moving car, bring it to a stop as quickly as possible, but stay in it. Okay? The car's springs will absorb some of the shaking and thus offer you protection. Now, if you happen to be under an overpass, don't stop there, okay? If there's an earthquake, it could be coming down. If you're in the open road, pull over, get off the road. You don't want, to be in any harm's way, but stay in the car, because it will offer some protection. Now that's during the shaking. That's going to be over with. It might seem like a long time, but it will be pretty quick. Then after the shaking, check but do not turn on utilities. Okay? Don't say, hey, we need the lights back on. Where's the power box? Let's see if I can get them on. If there are any shorts and things like that, you don't want that to not be a short anymore. Yes?
Is that because the wreckage or the earthquake will have break apart like wires and then they get accidentally shocked or something?
There's that. The falling power lines, there could be breaks or exposed wires, and you could be zapped by that. In fact, if you happen to be in your car and the wire falls across the car, right, don't get out. That's exactly right to say, oh, okay, it may not be hot because I don't feel anything. Well, guess what? You're insulated. Rubber tires, okay, you're fine. But as soon as you get out, you provide a pathway to ground, and you become part of that pathway to ground, and you're dead. I mean, you're toast, because you now have provided a way for that to get. So yeah, don't get out of the car if there's a wire across your car. Stay in the car until someone gets it off. Okay. If you smell gas, by the way, natural gas doesn't have an odor. They add an odorant so you can smell it. Okay, it's something that's pretty noxious too. So if you smell it, open windows, shut off the main valve if you know where that is, leave the building. Report the leak to the utility. Don't re-enter the building until you know it's been checked out by the authorities. If the water mains are damaged, shut off the main valve. If electrical wiring is shorting, close the switch at the main meter box. Okay? Know where all that kind of stuff is, especially if you live in an area that could be wrong. Turn on your radio or television if you have power. If you don't have power, it's a good idea to have one of those portable radios that runs either on batteries or you can wind them up and generate your own thing. Good for weather situations too. Stay off the phone except to report emergencies. Because guess what? Phone lines go down, cell towers go down. This was probably written before there were many cell towers. And you have limited lines available. The emergency people need those lines. You don't need, hey, did you feel that? Wow, that was something, wasn't it? That doesn't do anyone any good. Stay off the phone. Stay out of severely damaged buildings that could collapse during the aftershocks, which could come from minutes later to maybe hours later. Okay? I've heard many times where there's been a major earthquake, people are afraid to go back in their homes the next night because the aftershocks could be as much as several hours later. Okay? Don't go sightseeing. Now, this actually did happen with some of the major bad tornadoes we've had. People, oh boy, I heard that Pleasant Grove got it. Let's go see. No, okay. number one, emergency vehicles need to be going through there. You don't, okay? Number two, if people are in shock, they don't need a bunch of people gawking at them. So, oh, look at that. You just don't need that. Okay. So stay away from those areas. You remember when the tornado hit at, was it Oak Grove? This was well before the big ones. Yeah. Okay, remember that? I'm pretty sure that was the time my wife's worked at Children's Hospital, and her office had a window that looked out onto Cooper Green. Now it's called Cooper Green Mercy. And she said it was just devastating. They had brought in 18-wheelers to act as morgue because they had filled up the morgue. You don't want to be driving through, say, oh, there's a lot of, no, you don't want that. That's not necessary. Okay, so that's just the mostly common sense type thing, but it's good things to think about ahead of time. Okay, so Mercalli scale was still relative intensity based on destruction. Okay, so finally they came out with the Richter scale. Now, where do you reckon Richter's from? Charles Richter, by the way, good name. Where from? Caltech, California. They are pretty serious about quakes. He's a U.S. American. Mercalli, I think, was probably Italian. You know, whatever. This was a good old American. He based it on the swings of the seismograph recordings. In other words, how much disturbance in the Earth's surface did it actually cause? That's the best scale. Now, this is a logarithmic scale. Does anyone know what that means? It basically is measuring the powers of 10 that you're experiencing. Okay? So if you go from 1 to 2, you're going from 10 to 100. If you're going from 6 to 7, you're going from 1 million to 10 million. So one on a Richter scale is 10 times that on the actual scale. And some things actually 30. Okay, we'll talk about that in just a second. So that's what it means. It takes a wide range of numbers and puts it onto a fairly small scale. And it's multiplied, not added. Okay, multiplied. Now, on his scale that measures the movement of a seismograph, you can see a seismograph move and see a 1 and a 2, very, very weak. Even a 3, you aren't going to feel it. Whereas on Mercalli's scale, that was a 1 that you weren't going to feel. So it's a lot more sensitive. Now, the largest measured so far has been a 9. Maybe a 9.1 or 2, I don't know. And I think the largest ever recorded so far, the last I heard, was one in Alaska. And this was back before Alaska was very well developed. And it was such a major earthquake, the tsunami from Alaska made its way all the way to Hawaii and did major damage there. That is a powerful quake. And that was up there around 9-ish or so. Okay? And so, yeah, it's pretty major. And the difference between 8 and 9 is 10 times, up to 30 times as much. We'll see that in just a second. Okay. So here's generally what you can think of with the Richter scale. 0 to 2, smallest detectable, you're only going to detect that on the seismographs. No one else is going to feel it anyway. Okay. 2 to 3, detected and measured, but generally not felt. Also on the seismograph, it's there, but no one's going to really feel that. 3 to 4, felt a small earthquake, but no damage occurs. Now, we talked about not all the earthquakes happen on the fault lines. Remember the one in New Madrid, Missouri, a major, major quake. Okay, that was 1811. I wasn't around for that. Okay, I'm serious. Okay, now There was one fairly recently, I'm going to say within the last 5 to 7 years, that happened Northern Virginia, I think, or somewhere there. It was enough that it caused some damage to the Washington Monument. And for several years, no one could go into the Washington Monument. They have stairwells in there, I think they have an elevator, and you could climb to the top and look out and see all of Washington, D.C. For 2 or 3 years, you couldn't because they had to assess the damage and make sure it was safe. So it did do some minor damage. I don't think there was any deaths or anything else. But that was somewhere in Northern Virginia, near D.C. My parents' farm, and now it belongs to us, the 4 kids, because both of my parents are dead, but we had built a house over on the farm so that when we went over to take care of business, we'd have a place to stay. My siblings all lived over there, but when their families were in, there just wasn't room. So we built a house, and we may retire there anyway. We wanted to build it while we could still afford to pay for it. So anyway, we have a house over there. And Karen's sister had given her a thing to hang on the wall that just said farm. Not very creative, but yeah, so we hung it up in case she ever came to visit, she'd see it. And when we went there the next time, it was down on the floor. I thought, who knocked this off the wall? I mean, why would someone knock this off the wall? So we asked my sister-in-law about it, and she said, oh, that must have been the earthquake. She said they just barely felt things, but they did feel a little bit. That happened, a very minor quake, probably a 3 to 4 in Northern Virginia, but they still felt it in Georgia. Yeah.
Is it true that we get earthquakes here in Alabama, but they're just like really, really
Yeah.
minor?
I bet you we have some of these that you can't even feel. And maybe some that you can, maybe just a few in there. It used to be in the Midwest, they'd have little ones once every 2 or 3 months or something like that, just a little something. Since they've been doing the fracking, people are almost constantly, not constantly, but very frequently, much more frequent and much stronger. So we have messed with Mother Nature and she doesn't like it. Okay. So, small earthquakes, no major damage occurred. 4 to 5, that may have been the one in Washington, D.C., that did some local damage. 5 to 6, moderate earthquake with structural damage. I doubt it's the one in D.C., but that was structural, so it could have been. But no other buildings I heard of damage. 6 to 7, strong earthquakes with some destruction. 7 to 8, major earthquakes, extensive damage and destruction. 8 to 9, great earthquakes, and where it happens, pretty much total destruction. I'm trying to remember the quake in Haiti, I think was around in this range, and the one in Chile was around in that range. I may be wrong on that, it may be in your text, but it was quite a bit of difference. And remember, every number you go up is 10 times as powerful. 1 digit you go up, 6 to 7, 7 to 8, it's 10 times. 6 to 8, 100 times, okay? So it's getting big, I mean, really big, really fast. Okay, so, let me see if they say that on here. Okay, now here's the part that sort of drives me nuts. I was thinking this was a later chapter. Wait. No. That I was training to read, yeah, it's on the slide. And I forgot that. I thought that was in the tornado chapter they did that. This is on this one. There's everything we just said. Okay. Actually, they've shortened this a little bit and made it much easier to read. So I'll leave it up there a little bit if you wanted to get that. But I was looking for, does anyone need that? Okay. No. Okay. Let me get this because this is important. By the way, Charles Richter, seismologist from California Institute of Technology, Caltech, in the early 1930s. and he based it on the swings of the seismographs. An increase of 1 on the Richter scale, this is on page 492, bottom of the first column, top of the second column, means an amount of movement in the ground increased by a factor of 10. The amount of movement in the ground increased by a factor of 10. The amount of energy released increased by a factor of 30. One change on the Richter scale, 1 digit there, 2 to 3, 5 to 6, increased by a factor of 10, but the energy increased by a factor of 30. So let's look at example 19.5. Compare the energy released by an earthquake of 7.2 magnitude to an earthquake of magnitude 5.2. Energy, what would that be?
When the plates, after they shift, they release the energy.
Say that again.
When the earthquake happens, when the plates shift, they release the energy.
Yeah, okay, that's what it's talking about. The amount of shaking, that's a factor of 10 for one change on the Richter scale, 1 digit on the Richter scale. But energy is 30 times because it takes 30 times the energy to shift something 10 times. Okay, so because a lot more energy is involved. So what would be the energy if you went from 5.2 to 7.2? How much more energy? Scale. Second, 900. 30 for 1 point, and then 30 times 30 for 2. So that's 900 times more energy. Whoa, okay. 100 times more movement, but 900 times the energy. And then it says compare the amount of movement of the ground surface wave amplitude associated with 2, that would be 100 times. So I already answered that. All right. Tsunamis is mentioned too. And I was thinking maybe this new book would have that about the Haiti thing, but I don't see it. So it doesn't have it in there. I was thinking it might, but it doesn't. Okay, now we move to 19.4. Origin of mountains. Okay, what is a mountain anyway? Some part of the Earth's crust is risen above the other part of the Earth's crust. Elevated parts of the Earth's crust rising abruptly above the surrounding surface. Okay? Now, if you drive from Mobile to Birmingham, basically you're going up in elevation. That's not a mountain because it's gradual. Okay? But from, this isn't much of a mountain, but from the valley below to Shades Mountain or Double Oak Mountain or something, that's pretty abrupt, okay, when the roads go up pretty steep, okay. That's what a mountain is. It's created by folding and faulting of the crust. The very things we talked about before. Either the crust was folded or it faulted, okay, and they'll call them folded mountains or fault block mountains, okay. There are 3 basic origins. As we said, folding, faulting, and the third one that they don't mention here is volcanic activity. The volcano keeps erupting and making higher and higher. Okay, now, there was a really cute movie, pretty funny movie, actually based on something real. The name of the movie is not a very short title. It was The Man Who Went Up a Hill and Came Down a Mountain. Do you remember that one?
Well, I'm a homeschooled child,
Right.
And there's, I don't want to be embarrassed to say this, but there was a VeggieTales short called The Englishman That Went Up the Hill and Came Down with All the Bananas.
Oh, I see. Well, that was, Hugh Grant was in it, and he's always pretty funny. It wasn't a comedy, but it had its moments in it. But what it was, I can't remember if it was Wales or Cornwall or somewhere in England, and this community was real proud of their mountain. And the British Geological Survey was going around doing their job, taking measurements and stuff, and they found out this mountain was 6 or 8 feet too short to be classified a mountain because it didn't go up abruptly enough. So they were going to take it off the map as whatever the name of that mountain was. Well, that's how everybody knew of their town. They were the one by this mountain. And now it wasn't going to be a mountain anymore. So the community got together and started hauling debris, rocks and stones and soil and everything else, and worked together as a community to increase the top of the peak until they got it that extra 6 or 8 feet high, and then they had the mountain. So that was what the story was. So it has to go up. A volcano does that itself. It adds stuff, not all the time, but periodically. Okay? 3 types of mountains: folding mountains, faulting mountains, and volcanic activity. So let's look at the folded or faulted mountains first. Some of these are called domed mountains. They begin as a broad arching fold. And what do you call it, arching fold? Anticline. Very good. Okay? A broad arching fold. That's how they begin, and may just keep growing over time. The overlying sedimentary rocks typically sort of weather away, leaving more of the resistant granite peaks. Granite is what kind? Say again? Igneous, exactly. More resistant granite peaks. Okay? And basically, if any of you have traveled to Tennessee and North Carolina, the Great Smokies, those are folded mountains predominantly. Okay? Predominantly. Okay? Began as these arching folds, and they are actually not growing. If anything, they're weathering away and becoming more rounded. They're old mountains. They're some of the oldest mountains on earth. Okay? And they are actually weathering away and probably getting shorter over time. But they're still mountains. Pretty major and beautiful mountains, by the way, too. Okay. And by the way, on page 493 is a picture taken from way up high. I think this was a Skylab photograph of the folded structure of the Appalachian Mountains revealed by weathering and erosion, obvious in the Skylab photograph of the Virginia, Tennessee, Kentucky boundary area. The clouds over the Blue Ridge Mountains are over the Blue Ridge Mountains up there, and you can almost see why they were named Blue Ridge, Smokies, you can sort of see if you've ever been there. The clouds hang so low that it just always looks smoky. It's not smoke. Most of the time it's not smoke. It's clouds. Okay? This is how it would begin. This is sort of showing the dome. This almost looks like that picture back from Sundance we saw several slides ago. You have the pressure coming up from below, probably, and we'll talk about this right at the end of the chapter 2, some sort of thing that's pushing up from below. You're folding the surface. This is largely sedimentary here. There may be some igneous somewhere under there, but anyway, largely probably sedimentary. Doing that, it breaks the surface because it's getting stretched more, and then it erodes easily, and then underlying somewhere down here is the igneous rock. That remains, and the rest is mostly been weathered away. But if this kept growing, then you would ultimately become a mountain. Okay? Yeah.
I can remember, back in the day, that they said that the Appalachian Mountain was still growing because they were pushing it up. So
And
now
then
you saying they're not growing
well, they probably are growing some, but also weathering processes are eating them away. Who wins, I don't know. Okay, Because both of those are very slow processes. And if the weathering is happening more rapidly than the folding from the pressure, then they're actually probably getting a little shorter. But some areas it may be the pressure is growing, especially if it's more granite up there, it's not going to weather as fast. So it varies. But what I was trying to mean, if you look at the Smokies, they're all rounded mountains, meaning they've been there a long time, and the jaggedness that you would normally see. Go out west to the Rockies or the Sierra Nevada, very jagged mountains. Those are fault mountains mostly, and they are still growing because of the pressures. Himalayas still growing because of the pressures. Yeah. I had often heard that the Appalachians are probably shrinking, but they could still be growing, but just eroding faster than they're growing. So I don't know for sure. That might be a good paper topic, if that's what interests you. Okay. All right. The fault block mountains, on the other hand, those rise really sharply along steeply inclined fault planes. Okay? Remember, your fault planes can be normal faults where the hanging wall is sliding down, or reverse faults where it's being pushed up. Okay? But they rise sharply along those steeply inclined fault planes. The thrust faults don't form fault block mountains because they're very shallow. They're not steeply inclined. They're very shallow inclined. The weathering erodes the sharp edges, so the older the mountains, the more rounded they are. The nearer the mountains, the more sharp and jagged the peaks seem to be. Red Mountain, very rounded. Okay, most of the mountains around here are very, very rounded. Okay, this is the picture showing that. Now, remember what we called these things? Ravens and horse. Not that you'll ever use such words anywhere in normal language, but that when they first happened, pretty sharp, distinct, faults. You can tell that. But over time, especially on the edges here, they get weathered away. Wind, rain, all sorts of things weather the edges down, and then the weathered materials fall down into the valleys, and so you get less steep. And this could be what happened to the man who went up a mountain, up a hill and came down a mountain, is that the over time it actually got shorter, but maybe no shorter here, but shorter compared to the surrounding thing. So that's what makes the, if you remember how it was defined, okay, there it was. Rising sharply, elevated parts of the Earth's crust rising abruptly above the surrounding surface. Okay? If you go back here, when this fault first happened, that was a very abrupt rise there, pretty tall there. Over time, it's not nearly as abrupt. It's a lot more rounded, and the difference, because this is filled in and that was worn off, the difference actually got much smaller. Okay? So, weathering does erode the sharp edges. So you can sort of tell the age of a mountain by how rounded it is. Now, there's other features, other characteristics of it. The Rockies don't get nearly the rainfall we do, okay, at least on one side of them. So everything weathers faster here. We have higher temperatures. The Rockies are typically lower temperature. The higher the temperature, the faster it weathers. This is going to be next chapter. But so it's not just how old they are, it's also how much weathering has occurred. So now let's look at volcanic mountains. Okay? These are the ones everyone always pictures. Okay? A volcano is a hill or a mountain formed by the extrusions of lava or rock fragments from the magma below. See, when that magma erupts, it doesn't just form magma, bring magma up. If it knocked off rocks, those get thrown out too, so it can be rock fragments as well as magma. Now, I find this really lacking here. The structure is a vent, a crater, and lava flow. and yet they don't illustrate that unless they do in this new book. I don't think they do. The closest I can come to it is the figure 1921, and that's just one sort of, the vent is where the lava actually reaches the surface. The crater is the hole where it comes out, which you can see underneath that, and then the lava flows, those are the layers that you have around that. So they say that here, and nowhere do they show an illustration of it, which I would think would be helpful. Does anyone know what that is? Mount St. Helens. Are there any of you old enough to remember that? Probably not. Huh? 1980. Any of you alive then? Okay, a few of you. Okay. Okay. 1980, Mount St. Helens erupted. I was alive then. Okay. Erupted, and it was probably the most recent major eruption volcano here in the U.S. Okay? You think it got taller then with all that lava coming out? It actually got shorter because when it erupted, there had been a crust that had been extinct or inactive for decades, if not centuries. Okay? So it had a lot of buildup of hard rock there in the crater, and when the eruption happened, it blew it off and blew off the whole side of the mountain. Okay, so it actually went down in height.
Did it create like this acid rain cloud?
Oh, yeah. Now, since then, and since you mentioned, I think I mentioned this before, Iceland had a really fairly major eruption because it's a volcanic island, and the dust and grit that were blown into the atmosphere, as well as acid rain and stuff like this, it was major enough and blew toward England. Okay, they're not really all that close. There's Iceland and there's England. There's Ireland and Scotland and Wales and the United Kingdom. The winds just happened to be going that direction. They had the ground flights at Heathcliff or whatever Heathrow Airport, the major airport in London. In fact, just about all the major jets in several areas here, sometimes even in Paris and stuff, they had to ground them because they did not want the plane sucking in that grit because it would damage the engines and could knock them out of commission in mid-flight. Not a good idea. And those were expensive engines and expensive planes. So they grounded things for 2, 3, 4, 5 days, until all that got out of it. And then I bet you the thing of acid too, that wouldn't be particularly good to do to the blades in your aircraft engine either. So this is Mount St. Helens, and you can just almost imagine that the lava flow, you can see where the flow went down here. That's the vent. The vents are anywhere the steam's coming up there. This is the major crater here, and then this is the lava flow. They don't illustrate it well. Now, this was an area that was highly wooded, and of course when you have molten rock going down the side of the mountain, wood doesn't stand a chance. So most of the trees burned up. And how far it went and how much it went, I don't know for sure, but it wiped out a lot of the agriculture anywhere around there for a few years. Bad news, right? Except that new soil, the dust and other things that came out of that, had minerals in it that weren't there before, that had been used up before. So within 5 or 10 years, they had record crops as the apple trees and other things were replanted. Now the soil is much richer than it was before. Mother Nature knew what she was doing. It was bad for short term, long term, a very good thing. Pretty good thing. Okay. Mount St. Helens. there are, guess what? 3 major types of volcanoes. The first of these, not very impressive sometimes, are the shield volcanoes. Constructive of solidified lava flows, that's basically all they are, broad, gently sloping cones. The one you see in figure 1921, the picture on the top, let's see if that's in here. Yeah, there it is. This is a shield volcano. Not very impressive, okay? Notice this is in Hawaii, this one is, and the earliest eruptions deposited lava here and then later here and here. All that was below the surface. You didn't even maybe know it was there unless you had some infrared or something you could sense it. At some point, it actually broke the sea level, and now it's just this big, gradually, broadly, gently sloping cones. That's all it is. I wish they didn't use the word cone. It's kind of like a shield. This, I think, is Mauna Kea or Mauna Loa. Mauna Loa in Hawaii. Okay? You can tell there was, sometime or another, here was a crater. There was one there, maybe a little one here, one there, a little bit bigger, you know. So it had several places where it came up. Some of these may be what we call vents, and the bigger ones are craters. I don't know. They don't ever explain that. But you can tell it's just lava rock. And, you know, maybe it's not erupting now, but it hasn't been that long since it has. If it erupts again, it's just going to continue building broad, gently sloping cones. Shields, let's call them shields. Because the next kind of volcano is called a cinder cone volcano. Now, it's not constructed just of lava flows, but mostly of rock fragments. That's why it's called cinders. Because when it blew, the cap that was in there, that was solidified, that's what mostly gets blown out. A little bit of lava, but mostly the rock fragments, the cinders. Those are steeper, but smaller than the shield volcanoes. So they go up more rapidly, but they tend to be not covered through the area. Nice little volcanoes. Unfortunately, I don't think there's a single picture of a cinder cone volcano here. Oh wait, they are. In the new edition it is. This is on page 496, 1922. Sunset Crater, a cinder cone volcano near Flagstaff, Arizona. Pretty small, but fairly steep. Okay? But then, we don't have it in the slide set, but it is in the book. They added that in this new edition. Okay? Then the composite volcano. Okay? These are the massive, monstrous, beautiful volcanoes when they're not erupting. Okay? Composite volcano, alternating layers of cinders, ash, lava flows, volcanic mud, just lots of stuff, and they build to great, large, majestic mountains. Somewhere up top is the crater. They don't show vents. I don't know if this is considered a vent. I don't know. Don't quite understand that. And then these, of course, are the lava flows. You have older ones and younger ones. More recent ones are near the top. It just keeps growing and growing. Of course, after a while, they sometimes are years, decades, maybe even centuries between eruptions. Okay? I'm sort of guessing here. I'm guessing that is the crater. Evidently, the last eruption blew off this whole side over here. I think this is Shasta. I believe that is Shasta. That's a different picture in your book, but I believe it's Mount Shasta. That's in Northern California. Okay? And it probably hasn't erupted in centuries. Okay? It's still pretty massive mountain. Okay?
Is it still active though?
What's that?
It's not active though.
Not active. I don't think so for, like I said, for several centuries.
I got my question. When they say they're not active, does it ever mean that it can't become active again?
No, nothing says it can't become.
Oh.
That's why I don't like they'll use the term sometimes extinct volcano.
Right.
Extinct to me says it's not going to come back.
Right.
So that's why I say a non-active
As long as
volcano.
Earth's still there, it's a possibility of.
Mount Vesuvius, I guess, had been inactive for probably centuries, and villages and communities are built all along the side of it, named Pompeii, ring a bell. And when Vesuvius blew, it covered the whole city. Many years later, people had even forgotten there had been a city there, and some archaeologists were down there studying stuff and discovered the whole city of Pompeii in the lava flow of Mount Vesuvius. So yeah, it's now. I wish I had thought, I didn't know we were going to get this far today. When we were in that week between summer and fall, my wife had meetings in Utah, near Salt Lake City, Park City, Utah. And so we went up for the whole week. She had meetings just Thursday through Saturday. So we went up for the whole week. And one of those days we went to Yellowstone. And there was a book that that we bought there that talks about the geology and everything of Yellowstone. And it is amazing. I mean, Yellowstone has all these geysers and all the paint pots and just all this just incredible geological wonders that are there. It's a big park, but I mean, you can drive along and just see thing after thing after thing. And much of Yellowstone, in fact, there's a huge lake called Yellowstone Lake that is just part of a crater of an enormous volcano. And that's why they have all these geysers and everything else, because all this geological activity is not that far from you. And it seems like I heard sometime fairly recently that they are afraid, and I thought maybe one of you said it, that the activity is picking up enough that they are fearful the whole thing could go. So it is an enormous crater. And I mean, on our map, it showed the map of the park, and it showed the, I can't think what they called it, kind of the contour of the crater. And it was amazing. When we were driving through the park, we went over we'll do this in a later chapter, the Continental Divide 3 different times. So when we were driving on this part, all the water from the rivers and streams and stuff were going down toward the Gulf of Mexico. Drive a little further, they're going to the Pacific Ocean. Drive a little further, they're going back to the Gulf of Mexico again. You're right at the place where waters are going opposite directions. So sometimes you drive along and the water's flowing north, and somewhere not much longer it's flowing south, you know. But they're going completely different places. Okay. So that will be really scary and so sad if Yellowstone blows up. Yo. All right. Other features. Now, there's a blurb at the top of page 497. It's a really good blurb. Volcanoes change the world. Okay? Now you think a volcano is just going to change a little area around it, right? They actually read this. It's pretty incredible. One of the strongest volcanoes ever, Mount Tambora in Indonesia. It talks about how much that influenced not just Indonesia, the entire planet, or at least the northern hemisphere. They also talk about New England had snow in June because of that eruption in Indonesia a few years later. I mean, it's just amazing. El Chicon in Mexico, 1982, cooled global temperatures by a few tenths of a degree for 2 to 3 years. Then they came back. But, I mean, that's pretty major. And in June 1991, the Filipino volcano, Mount Pinatubo, erupted, blasting twice as much gas and dust into the stratosphere as El Cajon had done, and the dust from that remained in the atmosphere for 10 years. So yeah, you talk about stuff coming out, 10 years dust was in the atmosphere from that. When I taught this course probably close to 10 years ago, there was a woman in the class from the Philippines, and her home was near Mount Pinatubo, and she remembered that eruption. Pretty major. So she wrote her paper on that. She said, I'm going to relate to that. Okay. The other features part here, I can't see exactly where that begins. Yeah. It's 496 it begins. At the top of that page, that paragraph. It starts with shield, cinder cone, and composite volcanoes formed, blah, blah, blah. But only a small fraction of all the magma generated actually reaches the surface. And most of it remains underground, cooling and solidifying to form intrusive rocks. We talked about that before, as opposed to extrusive when it reaches the surface as lava. The igneous rocks described. Okay, so some of these other features start there in that paragraph, and I think maybe go into the next one, or mostly in that paragraph. And here's what we're talking about. Most of the magma doesn't make its way to the surface. It remains underground. It cools and solidifies to form intrusive rock. Okay? Igneous intrusive rock. Generally large crystal size because it's cooled slowly. Okay? Now, some of the features that it forms, this intrusive rock, would include the batholith. Okay, that would be a fairly large area. It came really close to the surface, but didn't break the surface. But over time, the surface got eroded away. It probably raised the surface, like those domes and stuff, raised it, but when it did, then it was easier for it to erode. And what you have here is where that sedimentary rock that was horizontal or nearly horizontal, it got pushed up by the batholith and then forms the hogback, which is jagged kind of stuff. And you'll have rocks here, different kinds of rocks on the surface. They're all sedimentary, but why are they so different? That's because the layers have been bent up like that. So that's one, a batholith. Large amounts of crystallized magma that formed underground, but then the overburden eroded away. But the igneous rock didn't erode, and that's what your batholith was. That's that. Okay, the stock is small protrusions from the batholith. So batholith is the big one, and ultimately will reach the top. The stock will remain underground. Okay, it tries to extrude, but either this stuff is too heavy or it finds a better outlet somewhere else, so it just remains underground. But there you're digging down and suddenly hit igneous rock, and you're right in the middle of sedimentary rock. Where did that come from? It was a stock. Okay? They don't, oh, there it is. The batholith intrusions can cause the hogbacks. That's where the sedimentary rock gets bent upward, and then you get sort of a ragged, jagged exposure of different kinds of sedimentary rock, but right in the same area. That's your hogback. Other related processes, okay? The dikes, okay? Those are the places where you have the vertical, the magma goes up a vertical weakness, a crack or a rift there, and when it goes up almost vertically, sometimes even gets close to reaching the surface or reaches the surface, there in the middle of all this sedimentary rock, suddenly you have some igneous rock because it's made its way very close to the surface and then as it eroded away. Yeah. Okay? The sill, on the other hand, the magma came up the dike, but then found a weakness between layers of the sedimentary rock, and you get horizontal layers where these are vertical, these are horizontal, those are called the sills. And imagine drilling down here, sedimentary, igneous rock, but it's not very thick. Go on down there some more. Okay. A laphalith will be sort of like a sill, but it was close enough to the surface, it forces its way up. That's one of those dome areas we talked about before, like Sundance Mountain was probably a laphalith. Maybe the very upper part was still sedimentary, but right below that you have the magma didn't quite get all the way to the surface, but came off the cliffs. Just like the batholith made it very close, but then the surface eroded away, and you have exposed batholith. The laphalith may or may not be exposed, but it's not nearly as big. And it came up the dike rather than, it was forming like a sill, but actually forced it up. These could be sort of like hogbacks here too, but they're a bit more obviously than this. So those are the other features that you have. Any questions? So what's the overall pictures? Okay. Now I'm not sure this exactly is in your book. Yeah, it is. Okay. Probably the last paragraph. Mountain ranges. Guess what? You can't say, oh, those are fault block mountains. These are folded mountains. These are volcanic mountains. Usually they're composites of all of them. I said the Appalachians were largely folded. You probably definitely have some faulted mountains in there as well. Whereas the Rockies are largely faulted. You may have a few folded, but you also have volcanic mountains in there too. So you can't say they're all. They're composites of many different processes, each uniquely structured. Folding, faulted, volcanic activity. You can tell on that particular mountain which it is. Okay? But even some of the pictures we saw earlier, definitely folding, but then you saw there's a crack there. That was a fault. Okay? After it folded, later it faulted. Okay? So it may be composites of many of them. These are especially apparent along the converging plate boundaries. Where plates are coming together, you gotta have this. That's why the Himalayas are there and growing. They're fault block mountains where the Eurasian plate and the Indo-Australian plate are converging together. Continental, they have nowhere to go but up. Okay. And by the way, there's been quite a bit of volcanic activity along the edges of the Himalayas. In China, they've had, it seemed like 2 or 3 fairly major volcanic, or earthquakes. It may have been earthquakes rather than volcanoes out there as well. Okay. Now, in the continental U.S., probably the biggest group of tornadoes, volcanoes are here. Okay? This is the west coast, the Juan de Fuca plate. Remember that tiny, probably the tiniest of the plates, pushing against converging with the North American plate. And it's subducting underneath. So somewhere under there, the oceanic plate is finally hitting hot enough material. It's melting again. You're losing that crust underneath there. It's melting, and if that is disturbing the surface any, look at what you got. The Song Peak, I don't know if that was a volcano or not. Mount Shasta is a volcano. Crater Lake in southwestern Oregon. Beautiful, from what I understand. I've not been there, but my nephew did. He loved it. Three Sisters, Mount Jefferson, Mount Hood. I know that's a volcanic mountain. Mount St. Helens, just below the Washington border. Mount Adams, Mount Rainier, that's inside of Seattle. Beautiful mountain. That's volcanic. Mount Baker is another volcanic mountain. Mount Garibaldi up in Canada. Look at all these, and that's who to blame. The one the Fuca plate pushing, subducting under the North American plate. Now, what's this dark area here? That's called the
North American.
no, this is all North American plate. These are the plateau basalts. Wait a minute. What are basalts?
Rocks.
Rock? What kind of rock?
Igneous.
Igneous rock. What's its color?
Gray.
Dark black almost. Very dark gray. Okay? That means it's high iron content. It's volcanic rock. Usually formed on the oceanic plate underneath the ocean. What is it doing here?
How did it get there?
How did it get there?
Yeah.
Well, it could be the ocean was once there, but when this subduction happened, these mountains cut it off, and that this was raised up. Yeah, amazing. Yeah, over a long period of time that happened. Now, this was something that I found totally fascinating. We were in Idaho along the Snake River. Snake River lines like they know why they named it the Snake River. And every time we got near it or passed over it, we looked down and the walls of the Snake River were vertical. Not like this, vertical. And I kept saying to Karen, how did they get so vertical? Why would they be such vertical walls? And finally, somewhere along the way, we ran into a place that we stopped and read. And you see, here's the Great Salt Lake. It's a pretty good sized lake, right? This was once just part of a much larger lake called Lake Bonneville. This is way before we were here. How they got that name, I don't know. But, and so a lot of this was probably under Lake Bonneville, which may have been part of the Pacific Ocean that got cut off when all this happened. But what made it a lake is that we'll talk about this in a later chapter, when the glaciers came down, okay, the glaciers act like bulldozers. This is in the ice ages. And they push ahead of them all this rock and soil and everything else, and they were coming down, pushing all that ahead of them, and then when they finally stopped, they started retreating. Of course, they were melting, feeding into this, or they may have been coming this way and melting back this way. That's probably what happened. Come in like this, and then melting going back, leaving a huge dam here of rocks and soil and stuff like this. Well, maybe they had a super rainy spring or something. That earthen natural dam gave way. And this huge lake dumped into what is now the Snake River and raced down there over weeks, days or weeks. And that rushing water from that enormous lake, that's what cut out the walls like that. Because they all went running down there and just dug a trench just like that. And that's why the Snake River is almost vertical wall. I mean, we would look down over the top and we'd see people in canoes down there and they looked like ants. I mean, it was that deep. Just incredible. All right. I think this is the last slide. Yes, it is. But before that last slide, there's people behind the science. And they mention here James Hutton. Must have been Scottish, Edinburgh University Library. Scottish natural philosopher who pioneered uniformitarianism. Okay? In other words, the principle of uniformity. That no, it wasn't some huge catastrophic events that happened in the past and now everything settled down from there. It's what's happening now, what's happening then, and it's continued to happen, will happen again, the principle of uniformity. So he's a potential paper topic. If you read on, you'll see friend of Joseph Black, William Cullen, James Watt. All those are pretty big, important scientific people. So you could write on any of them. You could, maybe if you want to review his book or Theory of the Earth, you could possibly write on that. So there's, just looking at this, there's Sir James Hall, and some of them were not good friends, okay? John Playfair, later Charles Lyell. There's a lot of different names there. Remember, this is not your paper source. This may give you the ideas, but you have to get your sources out elsewhere, the library, the internet, or somewhere like that. Okay. And guess what? Nothing replaces reading the chapter. Okay. So please read the chapter. It's better to do it before I talk about it. That way it'll make more sense to you. But if you haven't, then read it afterwards. This is one of the shorter summaries, okay? Not that huge of a summary. And the key terms, this is one of the shortest lists of those. Of course, they're listed alphabetically, but they give the page number on which you can find those. Okay, then applying the concepts, even though the other thing seems pretty short, there's 50 questions there, which is probably a little bit longer than normal. I think the best thing to study for your test would be those applying the concepts and multiple choice questions. Most of you, this chapter, your test won't be multiple choice. Sorry about that, but still a good thing to look at. The answers are given here, so you have that. There's questions of thought you don't have to do this time and for further analysis, but there's still great things to use as study guides. Parallel exercises, you can look at some of those if you want, especially those to do with earthquakes. They may be fun to look at. All right. What's that? Okay, yeah, it's a take-home test. Okay? And what it was, I found that the multiple choice questions were so nitpicky, tricky, that I didn't want to do it, so I rearranged them into short answer questions, and then so it's only one page, and it's only really 10 questions, but most of them multiple parts. So I think there's a total of 20 blanks, or 18, or something, 16, something like that. So it's still a full chapter test, but it's just, I just did not like the quality of questions that I found in the test bank. So I chose to do that. Well, okay. All righty. I guess I'll go on and pass out the test, and I won't pass out, but I'll just pass out the test. This is your take home. This is not the one we're doing tonight. We're doing today the one on chapter 18. Take that one. Yeah, this is These are not due until a week from today, but if you finish them sooner, you can turn them in soon. Okay. Next time we will have the lab. Now the lab is the chapter 9. Okay. It really doesn't have that much to do with chapter 19. It really is a lot more to do with what we did with the globe, latitude, longitude, that kind of stuff. That's our next lab. Yeah. Sorry?
We get to take these home.
Yeah, this is chapter 19 test, the take home. What we're going to do in about 5 minutes, we're going to start the chapter 18 test, which is not take home. That's the one we do in class. You can have your formula and equation sheet for that. If you don't have it ready, you can be working on it quickly. Okay? Now the question is, for 5 minutes, is it worth starting 20? It probably is.
Yes.
5 minutes.
5 minutes. No, just
What's that?
By the time you get it pulled up, it's going to be 5 minutes.
Well, that's what I was wondering. So let me see. There we go. Huh? You want to go and get started?
Yes.
Oh, y'all are so easy. Okay. So we'll start next time. Okay, the first 2.5 hours will be chapter 20, and then the last 2 hours will be the lab that goes along with chapter 19, though it really has not much to do with 19. Actually, a later lab will have more to do with that, but I'm trying to follow the labs from the lab book like they come. So it'll be a latitude and longitude lab next time, which is kind of a fun lab. So I think you'll have a good time with it. Probably won't take you 2 hours, but I'll allow you 2 hours to do it. Okay. So I will get out of this and end this.